All right, we are going live. And let me go ahead and turn the recording on. Okie dokie. Okay. There we go. All right. Just had to figure out how to turn the recording back on. Sorry, GoToWebinar is not our usual. GoToWebinar is a usual program for doing this, but we're using Zoom because it's easier to support a large number of people. So we will be taking questions in chat if you have any. Let's see. Hi, Craig. I'm doing great. Thanks for asking. Let's see. So we've got nearly 300 people registered, so we should have quite a full group today. So I've got both myself and another member of the Pettibridge team here to help answer some of our questions. So we'll go ahead and just get rolling. All right, let's see how many people we're up to. About 50, 60 inside the webinar so far. All right, that looks good. Well, just because we have a lot of material to go through, I'm going to go ahead and just jump right in to kind of covering our material today. We're also live streaming this on YouTube while we're at it. So today's webinar, Akka.Cluster Simply Explained. This webinar was inspired by some questions I answered in Gitter chat over the past couple of weeks. And these are questions that have kind of come up quite a bit over the past 6-7 years while we've been doing work in the greater Akka.net community. And I wanted to go ahead and try to provide a broad strokes overview of what Akka.Cluster is, when and how you would use it, and really what its sort of purpose is. What's the benefit of having this in your repertoire as a .NET developer? So let's go ahead and dive right in. So the first thing we want to address is, why does Akka.Cluster exist at all? This technology seems relatively, let's say, complicated compared to building a standalone CRUD application. Therefore, there has to be some business reason why this technology was created and why it gets used. So what are those? Next, we'll go ahead and talk a bit about some of the use cases. Who are some of the companies that use Akka.net? What are some of the, let's say, industrial use cases that they use it for? And what technical, let's say, traits do all of these business cases share? So we'll talk about that. We'll talk a little bit about the mechanics of how Akka.Cluster actually works. We're not going to spend a ton of time digging into this. We've got plenty of other material on our website and in our training courses that cover some of this, but I do want to provide kind of a big picture overview of that. And then the practical bits. How do I distribute work, state, and services inside an Akka.net cluster? And lastly, what are some of the things I need to bear in mind in order to actually go and deploy an Akka.net cluster as well? So we're going to try to cover all of this over the next hour and a half. Now, I want to go ahead and start with why Akka.Cluster. Why do .NET developers need to take a look at something like Akka.Cluster? Well, what's worth starting with is actually talking about how most business software is developed. For the past 30 years, our architecture for building any sort of, let's say, customer or internal facing application largely follows the sort of client server model, where you have a bunch of differentiated pieces of software that all follow a neat directed acyclic graph that basically kind of determines how traffic moves and how requests are handled throughout our applications. And so, we have a web browser, which is highly specialized. We have a web server, which is also specialized, and a database server, which is also specialized. And so a web browser is a client of a web server. Web server is a client of a database server. And then the database server forms what is known as the root dependency. This is where the source of truth tends to live inside these application designs. So the web server kind of plays a pivotal role in getting data from the source of truth and formatting it into a response type that the web browser can consume. That could be a JSON response over Web API, or it could even be server-side rendering, which is how dynamic websites used to operate for a fairly long time. Well, the problem with traditional app design is that it naturally forms bottlenecks and single points of failure. And it's almost always the database is where this pain starts to be felt. Because the source of truth is highly centralized in these traditional, let's say, CRUD architectures. As a result of that, it becomes very difficult to scale that source of truth as the demands in that system begin to grow over time. So traditional sort of, let's say, CRUD app designs, which are stateless, they tend to go ahead and concentrate their data inside a database. Their greatest advantage is that they're relatively inexpensive to build and relatively inexpensive to maintain. But this comes with a cost, and that cost is centralization. So by centralizing our source of truth in a single location in our network, or really, let's say, a single type of service in our network, most people who are running, let's say, SQL Server, for instance, do tend to use something like an always-on availability set or replication or some other type of let's say, fault tolerance mechanism. But those centralized, let's say, resources inside our network, even though we might be able to work around making them a single point of failure, they still become a single point of bottleneck, which is actually a more expensive problem to solve. Because as a result of the source of truth being concentrated in one place, every other service on the network needs to go to that location in order to do its job. And it's very difficult to scale around that. And it's pretty much impossible to scale that horizontally, unless you're using, let's say, a decentralized data store like Cassandra or Azure Table Storage or something. And that's kind of what we're going to move into in a little bit here, is we're going to talk about decentralization is one of the forces that's motivating users to go ahead and learn how to use tools like Akka.Cluster. So centralized applications, because they have these drawbacks all related to concentrating the source of truth in a small number of locations on the network, they tend to struggle under scenarios where there's a lot of demand for their software, and they tend to struggle in scenarios where there's high failover and fault tolerance requirements. Now, you can introduce all sorts of different changes to your architecture to try to mitigate some of these problems. So for instance, in an environment where you have, let's say, a very read-heavy workload, you can use things like caching to kind of help mitigate some of the pain there. In environments that have write-heavy workloads, you can go ahead and try using queues and single writer patterns to reduce lock escalation pressure and try to go ahead and improve throughput that way. So there's ways you can go ahead and mitigate some of this. But ultimately, the architecture itself is what creates these problems, and you can't really escape it. All you can do is buy yourself some more runway. But there's one problem in particular that a CRUD system can never do, can never really accomplish, and that's supporting real-time processing constraints. So in an environment where you're doing something like, let's say, building a multiplayer video game, or you're building a real-time foreign currency exchange trading program, or maybe you're building something like a monitoring solution where you're trying to monitor the health of some resource, or maybe you're trying to monitor fraud inside a payments network, that type of thing. Those environments and those types of problems are things that CRUD fundamentally can't support, because CRUD operates at a very high level of I/O, where you're hitting disk, you're hitting the network, there's a lot of serialization overhead, and you have zero chance of being able to successfully deliver a system that can do this under those requirements. In order to build an application that has, let's say, that has the need to go ahead and support real-time processing constraints, the source of truth must be decentralized. You have to go ahead and move the source of truth from living in, let's say, a single isolated service to basically living in the endpoints of your network itself. And that's what a decentralized piece of software can do. And decentralization, basically what that is, that's peer-to-peer networking is what decentralization is, where every node is equal in the eyes of the network, and every node is therefore capable of supporting the different types of work other nodes are capable of performing. So what decentralization gives us, and what it gives businesses that need it, is the ability to scale horizontally and the ability to not suffer from single point of failure and single point of bottlenecks type issues that their normal, let's say, client server applications have. So decentralization is really the driving force behind adopting technologies like Akka.Cluster. The big cost to decentralization is the fact that this makes application development more complicated. And the reason why is you have to be able to program each of these different, let's say, processes to be able to work with other copies of itself. And on top of that, in order to successfully decentralize your solution, you need to introduce a property to your software that is largely unheard of in client server environments. And that property is known as topology awareness. So in order to actually decentralize a piece of software, you have to create a peer-to-peer network. This means that peers need to be aware of who else is in the topology. In order for me to join a peer-to-peer network, I need to be able to have some way of discovering who else is in it. That way I can go ahead and establish some network communication back and forth between those peers. The way peer-to-peer networks tend to distribute work and distribute state is by constantly negotiating back and forth with each other. Hey, I need to find a piece of data somewhere else inside this network that will allow me to fulfill this request. Either that, or I need to go ahead and route the request to you and have you process it. So instead of having, let's say, traditional, 30-year-old technology like load balancers doing this work for us, the actual endpoints of the network themselves are performing these types of negotiations. So in a decentralized network, we become aware of our network topology, which means that new nodes can join the network and old nodes can leave. This gives us the property of elasticity inside our network, which means the network can expand and contract as a result of just, let's say, firing up new Kubernetes pods or new virtual machines, or really any other type of resource. We can go ahead and expand the network and then contract it on the fly without having to edit configuration. This is just something that the application knows how to do by virtue of its network protocols that are built into it. And we're going to talk a little bit about what those protocols are in just a little bit. The other thing that a decentralized network can do is, in addition to communicating about what the state of the network is, meaning which nodes are currently part of the network, which nodes are trying to leave the network, we also have the ability to distinguish which nodes are available to do work right now and which ones aren't. One of the things you need to have in order to build a reliable application of any type, whether it's peer-to-peer or client server, is you need to have the ability to react to changes in availability. So if a web server becomes unhealthy and can no longer respond to requests, the load balancer is going to notice that web server has failed its last 2 health checks and might pull it out of service and not route requests to it anymore, because we don't want to give our users a bad experience. Well, decentralized applications work much the same way. They have the ability to detect when nodes have stopped responding, and therefore they say, you know what, we probably shouldn't route any additional work to those nodes until those nodes are either kicked out of the network, in which case we'll just route that work someplace else, or we'll go ahead and wait for those nodes to come back. And whether and how Akka.Cluster decides how to do that can vary a little bit by workload, and we'll cover some of those too. Now, probably the biggest thing that's different about having a decentralized application is load balancer and application gateways and all these other intermediaries that you normally use for connecting stateless services together are total cancer inside a peer-to-peer network, because they interfere with the process of topology discovery. So we don't ever have them anywhere inside our peer-to-peer network. You can have a load balancer sitting on top of the peer-to-peer network, routing HTTP requests to a web API these nodes might expose. That's fine, but you never have one sitting in between the peers themselves. That's a total anathema to building peer-to-peer networks. Never something you ever do under any circumstances ever. So now the next big important point about how applications become decentralized is that, in addition to having this sort of notion of topology awareness, and by the way, this is what an Akka.NET cluster looks like. This is a type of peer-to-peer network design known as a mesh network, where every node maintains a direct line of communication to every other node. Now, the reason why Akka.Cluster is built this way is because Akka.Cluster is used to support applications that usually have soft real-time processing requirements. So for instance, if I'm working at a large bank and I have to go ahead and process, let's say, credit card transactions, or I have to go and evaluate loan applications or bank transfers or any other a number of, let's say, routine financial operations, I might have a requirement that says, I need to be able to know whether this transaction is fraudulent or not in under 100 milliseconds. Those are how those sort of soft real-time requirements tend to get expressed. Therefore, in a Akka.Cluster style network, in order to support those soft real-time requirements, I want to go ahead and make sure that I have a fast, direct line of communication to any other node I might need to work with in order to complete that request. Other types of peer-to-peer networks might use what's called an edge network, where every node has a finite number of connections to other nodes. The internet itself is organized as a series of edge networks that are all interconnected. Edge networks are great because they can scale to an infinitely large size. The only thing that happens is the more, let's say, the larger the network grows, the more network hops there are going to be between the two furthest points. And that's going to result in having to do a lot of, let's say, congestion and routing sort of algorithms to try to figure out what's the most efficient route to get from point A to point B. We don't want to deal with that in a real-time network. That's why we maintain direct lines of communication. The other reason why our network's built this way is to make failure detection instantaneous. If node D crashed, every node that had a direct connection to it would know instantly because all of their TCP connections would be blown up at the same time. So that's why we build it this way. And the downside of a mesh network is you're limited in terms of what the maximum size of the network can be, because each one of these TCP connections introduces a certain amount of memory overhead. And so the theoretical maximum size of an Akka.NET cluster is probably around 10,000 nodes. Biggest I've seen in the wild, I've seen plenty of clusters that are in the 1 to 200 node range. Biggest I've ever seen was about 800 to 850 nodes. And the JVM implementation of Akka, I think the biggest they've had was about 8,000 nodes. So these networks can still grow pretty large, despite the fact that mesh networks have these limitations. Now, the other way apps become decentralized is how the application performs versus how the database performs. In a traditional stateless CRUD environment, the database is that concentrated source of truth. All the traffic passes through it. Well, we're trying to explicitly avoid that in a decentralized application. So the role of the database changes pretty significantly. State is now something that is the responsibility of your application, not the responsibility of the database necessarily. The role that the database plays is that the database is now used as cold storage. It's meant to exist as a repository where information is saved so it can be recovered later by another node that might need to start up and, let's say, recover some business entities that haven't been used in a little while. Or maybe if we shut down this node and we want to go and move that state to this node over here, well, we have to have some way of doing that, and a durable store like a database or maybe a cloud storage system like Azure Blob Storage might be a way we go about doing that. So the database gets used in a much more, let's say, write-heavy way for the most part, and it's kind of just meant to be a parking space for storing data in a secure and durable fashion. It's not used for serving up all sorts of hot queries anymore. That all tends to be performed in memory by our application code. Now, the reason why we do this is so we can actually achieve those low latency requirements that we have. When you are using, let's say, application state as your source of truth, you benefit from a property known as state locality. This means that the data you need to do your work is local in memory to the code that performs it. Therefore, you're operating at a very low level of I/O. You're using essentially either your RAM or you're using your, let's say, your L1 or your L2 cache on your CPU if it's very frequently accessed data. Most of the time, it's just going to be stuff that's in memory. So that allows us to go ahead and perform things like real-time stream or event processing, where we can go ahead and react to changes in data at, let's say, millisecond or sub-millisecond latencies and produce results. If I go ahead and move down towards our use cases, I'll go ahead and talk about a couple of specific ones that some of our customers worked on, where they're able to process things like tens of thousands of concurrent graph queries per server with where they're computing essentially millions of possible results for this query. And they're able to serve up 1,000 good results in, let's say, under 5 milliseconds. That's something that a decentralized application can do when it's able to retain that sort of the full graph of everything that needs to be searched in memory. And it's not hitting the database every time to do that. So what Akka.Cluster fundamentally gives .NET developers is a framework for building decentralized .NET applications that can be highly available, highly fault tolerant, and achieve very low latencies. So the first thing Akka.Cluster does is it makes it feasible for us to create peer-to-peer networks of Akka.NET applications. So that's kind of the foundational part of what Akka.Cluster does. So it introduces some protocols that allow us to go ahead and let new nodes join the network and allows older nodes to leave the network when they need to be taken down for auto scaling reasons, or maybe they need to be taken down because we're about to deploy a new version of the code, any number of reasons. We also support the ability to describe changes in node availability. Now, by the way, when I use the word node, I'm referring to a single actor system. So an Akka.NET cluster is a network of actor systems that are all able to freely talk and exchange messages with each other's actors. That's all that Akka.Cluster really does. So it creates a peer-to-peer network of different actor systems that can all cooperate together to solve distributed computing problems. So we have the ability to subscribe to changes in node availability. So if a node gets too busy to respond, we'll go ahead and get an event that indicates this node is now unreachable. And tools like Akka.Cluster routers will go ahead and stop sending traffic to those nodes until they become available again. That's part of us trying to go ahead and use that topology information to stay available. And when I say stay available, I mean the entire network's going to try to make sure it can successfully process all of our end users' requests. That might mean having to steer traffic away from nodes that are struggling to stay up right now. So that's one of the things Akka.Cluster lets us do. Akka.Cluster also allows us to use a feature called roles. Roles are just a set of labels you can use to describe what each actor system is capable of doing. And it allows us to go ahead and build a heterogeneous cluster where different services that have different code bases and different actors can all participate inside the same cluster together. And we can use these roles to essentially separate our communication, where I say, I want my marketing automation app to go ahead and receive this data, whereas I might want my payments app to go ahead and send me this data back in exchange. And I can go ahead and use roles to figure out which peers in my network can perform which function. And then finally, we also have a little bit of technology in Akka.Cluster called clustered routers. These work the same as Akka.NET routers, but they actually go ahead and add and remove routees based on how our Akka.NET cluster network changes over time. So we can go ahead and if we add more nodes to the cluster, the routing table grows. If nodes become unavailable or they leave the cluster, the routing table will shrink. So this allows us to go ahead and dynamically include new nodes inside our ongoing work without having to program it ourselves into any of our C# or F# code. So that's one of the big things that Akka.Cluster kind of lets us do. And this is kind of the foundational part of the Akka.Cluster framework. There's a whole bunch of pieces that are built on top of it that we're going to talk about today, like Akka.Cluster.Sharding and Akka.Cluster tools that give us even more options for being able to build these decentralized applications. Now, why would you want to use Akka.Cluster to build a decentralized piece of software? Well, the first thing is that if you have to maintain state in the endpoints of your network, you have to have some way of reasoning about how that state gets modified. This is like a classic concurrency problem. Well, that classic concurrency problem is something that actors solve really well. They give us that sort of single-threaded, FIFO model for going and processing messages. And that makes it very easy for us to reason about how the state for any individual entity inside our cluster might be modified at any given time. So actors make that really simple. The second thing is that Akka.Remote makes it really easy for actors in different processes to communicate with each other. The biggest benefit of Akka.Remote, in fact, is location transparency, where if I get an iActorRef, which is the normal, let's say, unit of work for being able to send messages to an actor, that iActorRef can point to a local actor in memory inside the process that I'm running inside of right now, or it can point to a remote actor on a node I had never even heard of. It might be a node that joined the cluster and started sending me messages using distributed pub sub or maybe a clustered router. So Akka.Remote makes that cross-network communication really easy. And then we can use tools like Akka.Persistence to event source changes in entity state. All entities should have their own actor in Akka.net. We'll talk about that a bit more when we introduce Akka.Cluster. But we can use Akka.Persistence for those entity actors to make sure that all of these state changes for our entities are journaled to a durable store of some kind. Typically, it's going to be a database. And when we have to go ahead and move an entity from one node to another as a result of, maybe let's say taking advantage of new hardware that's been added to our cluster, or maybe because old hardware is leaving the cluster, Akka.Persistence provides us with a very simple means for being able to persist and recover that state without having to reinvent the wheel. Akka.Persistence is essentially a really nice abstraction over a lot of different databases, and it solves a bunch of problems that relate to, let's say, schema and versioning and so forth. It makes it really quite easy for us to go ahead and recover and persist state in a entity-specific fashion. Next, Akka.Cluster provides, this is probably the most important piece of functionality that Akka.Cluster itself does, is it goes and provides topology awareness directly to end users. Okay, I see some questions coming in here. Akka.Persistence to Google Firestore in the works, or am I stuck with MongoDB or Cassandra? Well, we support all sorts of different database options ourselves. So in terms of what Petabridge supports, we've mostly been working on recently SQL Server, Azure. We've been working quite a bit on Redis and MongoDB recently. Our Cassandra plugin's a bit out of date. We haven't updated it since like Akka.net 1.0. So that's probably not one I would recommend using right now. But we're always open to adding new ones. And we frequently go ahead and get asked to do that by some of our support plan customers. In fact, we just redid our entire Akka.Persistence.Redis plugin to support a Redis cluster mode at the behest of one of our customers. So we're always open to going and adding new platforms and adding support for those, but it just kind of depends on where the demand is for it. The last thing that Akka.Cluster will do is allows us to ship higher level abstractions, such as Akka.Cluster.Sharding, to simplify app development and deployment. Ideally, what Akka.net and Akka.Cluster tries to do is we want to give you a framework to make the right choices that are right for your business, and we don't want to hide what's happening behind the scenes. But by that same token, we also want to go ahead and try to give you some high-level abstractions that you can opt into, which will solve routine infrastructure problems for you. Now, let's go ahead and talk about some Akka.Cluster use cases. And by the way, for the folks who are asking on Q&A, I think I'll go ahead and get to that at the very end of the presentation. All right, but please go ahead and keep asking questions. I will make sure I address all of them at the very end of today's course. All right, so some Akka.Cluster use cases. Who are some people who use Akka.Cluster? What are the use cases? And what are some examples? So why use Akka.Cluster? How do you know if your business has a suitable use case where Akka.Cluster would be an effective solution? Well, the most common answer to that question is when you have a real-time processing requirement. That's the one thing a CRUD system can never do very well. And it's because of the let's say, lack of state locality is really the reason why that is. And so Akka.Cluster gives you a meaningful and solvable way of addressing that problem relatively inexpensively. So that's probably the biggest driver behind use cases. And so I'll give you some industrial examples of that in a moment. All the reasons why you might need to use Akka.Cluster is we need to be reactive. So I'll give you a good example. I did some work in the real-time marketing automation space in my last company. That's really where Akka.net came from. Our business requirement was that we already had, let's say, a successful real-time analytics product that we had built on top of Apache Cassandra. Cassandra, under the covers, was performing all the aggregation we needed to go ahead and serve up our real-time dashboards. But when we introduced the need to go ahead and react to changes in that data in order to send our customers' users targeted messages and offers, we needed to have some way of reacting to those real-time changes in individual user event streams. We looked at technologies like Apache Storm and Druid and a couple of others to do that. And they really fundamentally lack the ability to do this. This is where you need something a bit more bespoke, like an actor framework in order to help you accomplish this. Can't really be done very easily with off-the-shelf tools. Other reasons to use Akka.Cluster. We need to process many concurrent and possibly reentrant workflows. So to give you an example from our business, we're working on SDK Bin, which is a platform that's like App Store meets NuGet. And we have a lot of workflows that we're adding to be able to go ahead and add support for support plans. Well, those workflows often involve events that occur several hours apart from each other. And we have to design the system to be able to support tens of thousands of those concurrently. So we need a model that allows us to go ahead and handle bursts of events that all occur in a very short succession. And then we need to be able to persist that state, shut that actor down, and then recreate that actor again when another burst of activity arrives at some point in the future. That is another really good use case for Akka.Cluster, being able to go ahead and run these workflows. Now, there's some other scenarios inside our system where the workflows need to be more real time, such as when someone purchases with a credit card and we need to fulfill their order right away. That's one example there. We need to have high fault and partition tolerance. Now, there's a lot of tools inside the traditional, let's say, CRUD space that can help you achieve some of this, but none better than a decentralized system. And the reason why is there's no single point of failure in a decentralized environment. So by having, let's say, our ability to go ahead and distribute our state and our work and sort of our processing to many different equal nodes, basically equal in stature and equal in responsibility nodes across the network. If some of those nodes fail, we simply lose bandwidth. We don't necessarily lose availability. That's the big idea behind this. And then finally, if we need to process an extremely high and usually unpredictable volume of requests, then you need a decentralized solution. You don't want to be in the business of having to re-architect your software every 12 months to be able to go ahead and address, let's say, changes in your traffic patterns and usage over time. Now, there are some CRUD architectures, depending on what your read-write workload looks like, that can handle high volumes just fine. A good example, if you have an extremely read-heavy web application, output caching, HTTP output caching is probably fine for being able to handle that. But if you need to handle a large volume of dynamic writes that require let's say, a real-time response that is bespoke to each user, you're going to have a problem if you try to address that with a pure CRUD architecture. That's why using a technology like Akka.Cluster might be a good idea. So these are some of the common questions that end up pointing users towards Akka.Cluster. Now, I've got a list here of some of our customers that use Akka.Cluster. So for instance, we got Bank of America, not just customers, but really Akka users. We got Bank of America, BNSF Railway, United Airlines, Dell, Becton Dickinson, which is a gigantic healthcare company in the United States, ING, Zynga, and GreenTube. And these kind of run the gamut of a bunch of different industries. So some industry-specific use cases. We've helped a lot of customers with payments where essentially every single payment has its own little state machine. The entire state machine has to complete end-to-end with a success or fail within a relatively short window of time. And there might be tens of thousands of these happening concurrently throughout the network. Akka.Cluster is a pretty good tool for modeling that. Fraud detection, again, similar type of story. There's a workflow that has to execute end-to-end where we have to go ahead and run each, let's say, loan application or payment through some type of fraud model that can go ahead and detect it. And we need to be able to do that in a relatively short notice because someone might be literally sitting there at a point of sale system inside a store or any other type of business waiting to see if their payment goes through. So this all needs to be done in fairly short order. And then my personal favorite problem in the finance space, this problem also shows up in industries like sports betting and certain types of e-commerce applications. So for instance, this shows up a lot in travel, is dynamic pricing, where you have an asset that usually has a, is considered to be highly perishable, like a ticket to a sporting event, or maybe a seat aboard an airplane, or a position for buying a currency or an equity or a position in a bond, that type of thing. And you need to be able to go ahead and dynamically price that on the fly in order to make sure you get the best possible ROI. That's another good example of something that requires, let's say, these types of real-time sort of stateful flows to be able to be done reliably and at scale. Travel and shipping. We have a number of customers that use Akka.net and Akka.Cluster specifically for fleet and vehicle tracking, where they're keeping track of, let's say, cargo that might be on board a ship or on trucks or on trains. We also have a number of users that use in the travel and shipping industry that use, let's say, Akka.net for doing broad search, being able to go ahead and, let's say, find an itinerary that can work inside a very large time frame for a very small amount of money, and might include a bunch of different possible destinations. That's another example there. My wheelhouse is analytics. That's kind of where my background is prior to working in Akka.net. Stream processing is very common, where let's say you might go ahead and model an analytic workload as something that is processing streams of events as they occur in real time and is producing, let's say, real-time analyses. The entire monitoring space, for instance, can be architected this way. Bulk analysis is another type of analytic workload that can be done really well with Akka.Cluster. So for instance, you might have a ton of data that you have to go ahead and pull down all at once. So for instance, we have a lot of customers that, let's say, receive data payloads that are updated weekly, monthly, or nightly, potentially. And all of those have to be turned around and rendered before the next day because all that data is going to be used in downstream consumers at some point. So going and chopping that data up into lots of parallelizable units, spinning up your cluster and scaling it out, and then scaling it back down again once the processing is done is a really great way to use Akka.Cluster for building like a grid computing type scenario. And then in gaming, by this I actually mean video gaming, Akka.Cluster is very popular for building multiplayer applications. We have a lot of folks who build mobile video games that use Akka.net for doing things like building game lobbies, chat systems, matching systems, and even for controlling, let's say, NPCs in shared environments. Some other use cases, just to go ahead and call some of these out. Sports betting, we probably have in the order of, let's say, I don't know, 12 to 24 different sports betting customers just here at Petabridge ourselves. And Akka.net gets used for, well, really, Akka.Cluster gets used for market making and running the order books, and also sometimes setting odds. We have a lot of customers that use Akka.net for monitoring, and this runs the gamut from fraud monitoring to monitoring the health of patients to monitoring, let's say, oil field production data, and to also doing things like monitoring, let's say, total network traffic that might be going to web applications and that sort of thing. That's a highly reactive style of application, and you need to be able to guarantee that when you see a change in, let's say, behavior that's being monitored, you need to be able to produce a notification relatively quickly. Otherwise, the value of your monitoring service is pretty diminished. IoT, we have a lot of users that use Akka.net on-premise inside factory environments, for instance, for being able to go ahead and run, let's say, software for being able to work with PLCs and other control systems for working with devices downstream. And so Akka.Cluster is there in order to offer a little bit of redundancy and a bit of network topology discovery when certain parts of the factory are offline and others might be on. Marketing automation, so this includes things like doing reactive, let's say, customer specific marketing offers for things like email marketing. It can also include things like building banner exchanges, that type of stuff. Workflow management is another big one, building lots of, let's say, decentralized and distributed workflow systems. That gets used, Akka.net gets used in that context quite a bit. E-commerce, we have a lot of customers that run things like, let's say, fulfillment, recommendation systems, notification systems, all kind of on the backs of Akka.Cluster. And finally, we have some more abstract stuff like enterprise integration, where we have some customers that are in the business of doing things like scanning really large Active Directory structures to go ahead and figure out if users should still have access to these resources, 30 days if they're given them, and this sort of rules-based type stuff. And so they kind of use Akka.Cluster to scale up and scale down. Some other scenarios I didn't mention, we have in the analytics space, we have a lot of customers that do predictive modeling where they're running, let's say, Monte Carlo scenarios to go ahead and predict, let's say, the likelihood of a disaster occurring. They might use that in the insurance industry. They also use it in sports betting for trying to set the initial odds on a soccer match, that type of thing. So Akka.Cluster gets used in a ton of different contexts and a ton of different industries. And what all these use cases have in common is they tend to be soft real-time. So they have a soft real-time processing requirement. They tend to have a, let's say, unpredictable demand where the amount of work that might be asked on the system can be very small or very large at any given time. Therefore, you want to have the ability to scale your hardware linearly to go ahead and support that. And they also tend to have, let's say, high fault tolerance and high availability requirements as well. So these are all kind of the use cases that really unite Akka.Cluster usage across many different industries. Now, oh yeah, forgot about backplanes. Sorry, these are some fun technical ones. Backplanes, message buses, and caches. These are like pure technical solutions. If you've been following my Twitch stream, I'm in the process of building a collaborative drawing program where it's in Blazor. People can go ahead and essentially it's like multiplayer paint.net is what it is. I'm in the process right now of trying to construct a SignalR backplane using Akka.net behind the scenes. That's another example of a type of use case for Akka.Cluster there. Okay, how does Akka.Cluster actually work? What's the secret sauce behind all this? Well, Akka.net itself is organized into a series of different NuGet packages. We have our core Akka library, which everyone's on this call is probably familiar with. We have Akka.remote, which introduces networking. We have Akka.persistence, which gives us the ability to write durable actors who event source their state and can recover it from a durable store. And then we have Akka.Cluster, which is kind of the raison d'entrée for this entire webinar here. Akka.Cluster depends on Akka.remote, which depends on Akka. So all those dependencies will be pulled in implicitly. This basically provides the basis for all of the high availability networking that we're going to be talking about today. And then there's some other high level modules built on top of Akka.Cluster. So for instance, we have Akka.Cluster metrics, which allows all of the nodes in an Akka.net cluster network to gossip about their CPU and memory utilization by default, as well as some other custom metrics you might set up. And those custom metrics can actually be used inside a special group of routers Akka.Cluster metrics introduces, known as weighted routers. These weighted routers allow you to do things like route this work to the node with the least busy CPU, or route this work to the node with the most available memory. And so this tends to play pretty nicely with auto scaling. Next, we have Akka.Cluster tools, which provide some additional add-ons on top of Akka.Cluster, such as cluster singletons and distributed pub sub are both on top of it. And we're going to talk about both of those in a little bit. We have Akka.Cluster.Sharding, and Akka.Cluster.Sharding depends on everything on this list except for Akka.Cluster metrics. Akka.Cluster.Sharding gives us a very reliable way of managing, let's say, entities that are bounded inside a single actor. And it's highly fault tolerant. It's able to guarantee that there are no split brains for any of our entities. And on top of that, it's very good at doing what's called partition handoffs, where we go ahead and redistribute some entity actors from a heavily loaded node onto a more lightly loaded node without losing any messages. That's one of the things that Akka.Cluster.Sharding can do really well. And the last thing, and we're actually going to talk about this today too, is Akka.Cluster.DistributedData, otherwise known as DData for short. This is an in-memory replication system for Akka.Cluster that allows us to go ahead and use a special type of data structure called a CRDT, conflict-free replicated data type, to go ahead and maintain basically a multi-node mutable entity that can be updated in multiple locations on the network and all merged back together again into a single consistent view of that object. And we actually use this internally for doing a distribution of shards inside Akka.Cluster.Sharding. So the first big picture about how Akka.Cluster actually works is that Akka.Cluster works by networking multiple actor systems together. So an Akka.net cluster isn't some, let's say, super, I'd say super complicated distributed entity or anything like that. It's really just a network of different actor systems that all know about each other. They all have the ability to freely communicate back and forth. And these actors can go ahead and use the same tools that Akka.remote exposes, namely actor references and actor selections, to go ahead and communicate back and forth. So what Akka.Cluster primarily does in terms of its primary piece of functionality is allows each one of these actor systems to basically maintain some data about who are the other actor systems in the network with me right now, and what network location are they on, and what sort of roles do they have. And I can use that roles data to sort of determine how I communicate with each node. Well, not necessarily how, but who I need to communicate with for this type of work. And so here's what the actual code looks like for setting this up. So to go ahead and enable, let's say Akka.Cluster in configuration, I just need to set the Akka.Active.Provider equal to cluster. This tells our actor system to load all the clustering components when our actor system boots. I need to go ahead and set up some Akka.Remote binding information to basically specify here's the network address we're going to host ourselves on. And then I pass in a set of seed nodes. These seed nodes are going to be the initial nodes we contact in our peer-to-peer network in order to go ahead and try to join the cluster. That's what role these nodes kind of fill here. And then down here, I'm going to specify my roles, which is going to kind of be a set of labels other nodes can use for figuring out what types of work can I perform. That's really what that's for. And then down here in my code, I go ahead and I just parse my little HOCON file. I'm going to go ahead and replace my .NETty.tcp.port with an environment variable here. And then I'm going to start my actor system and then just create a couple of actors. So starting up Akka.Cluster is actually really simple. There's not a lot to it. And this is all you really need to go ahead and actually get a cluster up and running. This will go ahead and cause Akka.Cluster to launch behind the scenes. All of the actors responsible for opening network connections and all of the actors responsible for sending heartbeats back and forth in order to keep track of who is still in our cluster and who might be joining or leaving the cluster too. Now, some important notes about clustered Akka.NET behavior. This is probably the most important slide of the presentation. There is no magic behind the scenes here. So Akka.NET kind of departs from a lot of behavior you see elsewhere in the .NET ecosystem, in that we are very kind of strict on trying to not introduce magic. So we don't want to use clever reflection tricks or anything else. And so in this case, what I mean by no magic is when you call actor system.actor.of or context.actor.of inside an Akka.Cluster application, those actors are always deployed locally inside the same process you're running inside of right now. That's a good default. It means that you're basically able to exercise control over the locality of those actors. A lot of developers assume that we're going to go ahead and arbitrarily deploy it somewhere inside the cluster. We do not do that. Akka.Cluster Sharding, on the other hand, does do some of that. It might go ahead and transparently move actors around the cluster, but you have control over how that's done via how that's configured. And we basically expose that to you up front as part of your cost for going and setting up Akka.Cluster Sharding. But by default, whenever you call actor.of, those actors are always created locally. Next, routers at Akka.Cluster are always still local by default. We're not going to start magically turning your, let's say, pool or group routers into clustered routers just because the Akka.Cluster actor reference provider is turned on. That's all still local by default. Pretty much everything in Akka.NET is always opt-in. You as the end user have to opt in to using these tools in order for them to start running behind the scenes. We think that's safe from a maintainability point of view. And we also think that probably most closely matches what users expect. Next, the one thing we do is we will automatically connect to the cluster at startup. And we do that based on those seed nodes you configured. Now, if you don't specify any seed nodes, then we're not going to try to connect to a cluster at startup. You're going to have to issue, and you can do this in C# or F#, a cluster.join command in order to go ahead and join the cluster then. And you'll see some messages inside your logs that say, no seed nodes provided at startup. So therefore, we're waiting for an instruction from the C# or F# code on what to do about that. And so when we actually connect to the cluster at startup, it's going to go ahead and establish some of these system messages that Akka.Cluster relies on, namely heartbeats, failure detection monitoring, and gossip events. The gossip events are what basically drive the expansion and contraction of the peer-to-peer network, but that's it. We're not going to do anything else, nothing that really affects any of your user-driven code. The other bit is that internode communication is always opt-in. In order for you to go ahead and communicate with other nodes inside the cluster, you either have to receive a message from another node, in which case you might choose to respond to it, or you have to go ahead and proactively communicate to another node of the cluster through a tool like a clustered router or maybe distributed pub sub. So the initial state of an Akka.NET cluster looks like this. We have a couple of seed nodes, and then we have some non-seed nodes. There is nothing special about the seed nodes and the non-seed nodes from a C# point of view. It's totally just a configuration detail is all that it is. So these seed nodes know that they're seed nodes, and these non-seed nodes know about at least one seed node in their configuration. Ideally, you should have about 3 seed nodes is probably the ideal number. You don't want any more than that necessarily, and you probably don't want any less than that. 3 is probably a good number. So in this cluster, we're only running with 2. What makes a seed node is that it's basically usually one of the first nodes started inside the cluster, and its address gets baked either into other nodes configuration, or if using Akka.Discovery, which is a relatively new module that we've added to Akka.NET, you can dynamically discover nodes using something like DNS entries, or at some point in the future, we'll probably add support for tools like Console and the Kubernetes Service Discovery API, where you can go ahead and query a seed node list and get it back, rather than having to necessarily hard code it in your configuration. But a lot of users today just go ahead and basically take some static addresses, stick them into their configuration, and those are their seed nodes. That's also what Lighthouse is for, which we're not going to spend a lot of time talking about today. But Lighthouse is kind of meant to be a dead simple Akka.NET seed node. It's basically a headless Akka.NET node that doesn't do anything other than run Akka.Cluster. So the join process looks like this. All these nodes, including the seed nodes, are going to begin sending join commands to each other. This is going to start the process of opening Akka.remote communication and beginning the propagation of gossip. Gossip's the protocol that Akka.Cluster uses to share information about how the topology of the network is changing. And so as gossip gets propagated, usually the first seed node in our seed node list will mark itself as the leader, and it'll go ahead and begin receiving gossip from a bunch of these other nodes inside the cluster. And you'll see right now that node C only knows about itself and node A, node D only knows about itself and node A, and node E only knows about itself and node B. Well, nodes A and B know about a lot more nodes than any of them do. So it'll take maybe a few seconds. I think the algorithm for figuring out how long it takes a new node to join the cluster is the log base 2 of n, where n is the future cluster size plus 1, I think. And that's how many seconds it takes. So it should only, in theory, take, let's say, in a 1,000 node cluster, it should only take, I think is it 2 to the 10? Is it 1024? I think so, off the top of my head, but it should only take about 11 seconds to join a cluster that has 1,000 nodes in it, maybe 12 seconds. Not doing my best mental math this morning, but it's relatively fast. So those nodes should be able to go ahead and join the cluster relatively quickly. And so the cluster should be fully formed. All of these nodes have a direct connection to every other node. And the cluster is now in a steady state where all of these nodes can begin receiving messages from each other and can begin performing work. So a node is considered to be healthy and ready for work once it is marked as a up member of the cluster. So this gossip protocol is what really allowed that cluster to form. And gossip is pretty simple, and it's a highly compressed set of messages that are built into Akka.Cluster. And every single node in Akka.Cluster emits gossip to n random neighbors once per second. And so when a node tries to join a cluster, let's say node A is the only node in the cluster right now. When node B tries to join node A is going to notice that, hey, I'm the only other node in the cluster, and node B has been able to contact me. Therefore, I'm going to tell node B, okay, you are now a full-fledged member of the cluster. You can mark yourself as up, which means you're ready to do work. So A and B will continue to send gossip about each other at a rate of about once per second. When node C decides to join the cluster, node A is going to go ahead and notice that. And it's going to begin sharing gossip about other nodes with node C. And it's also going to share that gossip with node B. So both of these nodes are going to receive a notification about each other. And typically node C will issue connection to node B. And once node A, if node A is the leader of the cluster, once node A has noticed that node C was able to successfully communicate with node B, then node A will go ahead and turn node C into a full member of the cluster, so node C can start doing work. And this is important because basically this is kind of the process for how the cluster grows and shrinks. is this gossip protocol. So the gossip protocol basically is fairly lightweight. We don't gossip about, let's say, every possible message being sent between nodes. That would be extremely chatty and would add up to a very large amount of messages. What gets gossiped instead is really only changes in the topology of the cluster itself. So when nodes join the cluster, that gets gossiped. When nodes try to leave the cluster, that also gets gossiped. Likewise, if a node becomes temporarily unavailable, and this is usually because that node failed to respond to a heartbeat request in time. If a node becomes unavailable, it'll go ahead and get marked as such by one of the other nodes receiving heartbeats from it. And that node unreachable gossip message will be propagated to everybody else in the cluster. And that'll tell tools like Akka.Cluster routers to stop sending this node messages. So that'll go ahead and get propagated. But if that node becomes responsive again, then we can go ahead and basically receive a node reachable again message, and then that node can start receiving data once again from clustered routers and so forth. In gold down here, I highlighted metrics gossip. This is what Akka.Cluster metrics does. It actually introduces another flavor of gossip, primarily built around communicating about CPU, memory utilization, and really any other type of custom metric you might want to report inside your cluster. All of that kind of gets shared through a second channel that gets created by the Akka.Cluster.metrics package. Now, nodes exist inside one discrete member state at any given time, and states are monotonic, meaning that you can only go forward, you can't go backward. So a node begins in a joining state. After the leader in the cluster, by the way, the leader is an arbitrary node, and the leader just runs a small amount of code that none of the other nodes inside the cluster do, but any node in the cluster can be the leader. It's basically the job of the leader is just to tally votes. That's all that it does. So that leader is going to go ahead and say, okay, when every other node in the cluster has been able to be successfully contacted by this joining node, I'm going to mark that node as up. When that node issues a leave command and says, hey, I want to leave the cluster and shut down, that node will mark itself as leaving. The leader will go ahead and mark that node as exiting once everybody has observed that node trying to leave. And then after everyone has observed that node exiting, that node will go ahead and be removed from the cluster, and it'll be removed from all the gossip tables behind the scenes. But at any given time, if a node becomes unreachable, it can end up in purgatory right here. And this happens when a failure detector doesn't receive heartbeats in time from one of these nodes. When that happens, this node becomes unreachable, and we're not necessarily sure what state it could be in. That node can, in theory, still be working, or that node might be hard down, maybe because its hardware failed, or because the process crashed, or because there was a deadlock inside of it. And when that happens, Akka.Cluster has some code you can enable called a split brain resolver, or you can use a tool like petabridge.command to do this manually, where you can issue a down command, which is a way of force quitting a node out of the cluster. A down command does not require consensus of the leader. So if I go ahead and mark a node as down, that node will be kicked out of the cluster as soon as people see that down command being propagated. So that's something we can do to go ahead and evict unresponsive nodes from the cluster periodically when that does happen. Typically, when a node becomes unreachable, it's almost always a temporary issue. It's usually caused by big bursts in CPU or network utilization, but sometimes nodes can be permanently down when they're unreachable, and that's usually caused by hardware or software failures. So what you want to go ahead and do is have that down command ready to go in the event that it's a hard failure, and you want to just kick that node out of the cluster. So that's what that's for. Finally, we've kind of talked a bit about this. Akka.Cluster works by unanimous consent typically. So all the other nodes in the cluster need to agree on something before the leader can take action. That way we make sure we don't end up, let's say, splitting the brain on what the state of our cluster is at any given time. So if node D signals to its peers that it wants to leave the cluster and shut down, well, node D might randomly gossip that to node C. Node C might randomly gossip the information to node B. And node B might tell node C, okay, I've seen your gossip, thanks. And then node A might receive a notification that all the other nodes know that node D is trying to leave, in which case it'll officially transition node D's state from leaving to exiting. And then eventually it might issue a remove command to go ahead and purge node D from all the cluster data behind the scenes. So I'm bringing this up, this node transition data, because this is basically the fundamental driver of all the topology awareness inside Akka.Cluster. Now, without that topology awareness, we can't distribute state, we can't distribute work, we can't do any of the other nice, fun things that Akka.Cluster depends on. So it's fundamentally important to kind of understand what Akka.Cluster is really doing behind the scenes and why it does it that way. So that's what all this stuff was. All right. Now, it is possible in Akka.Cluster, by the way, to receive these topology alerts yourself. This isn't opaque. It's actually something you can go ahead and completely tap into on your own. And the way you can do that is you can go ahead and basically get access to the Akka.Cluster plugin by doing Akka.Cluster.Get, and you pass in a reference to your actor system. And then from there, you can go ahead and subscribe an actor to, let's say, the initial state of the cluster as events. So if there's 10 members in the cluster right now, you'll get 10 member up events if you do this. Otherwise, you can get the initial state of the cluster as one big snapshot that kind of describes everything that's going on all at once. And then I'm going to tell the cluster, I want you to send me any member events that occur in the future. Every time the topology changes, you'll get a new notification. This can be really useful for all sorts of things. All of the higher level tools in Akka.Cluster are all fundamentally built on top of this. Akka.Cluster, this little cluster object down here, also has a method you can use to query the current state of the cluster at any given time. And that'll go ahead and give you a point in time snapshot of what the cluster looks like. So you can go ahead and receive these topology alerts yourself and use them behind the scenes to go ahead and drive application specific behavior if you want. Most of our software that we're building for SDK bin right now doesn't actually do much of this. We're okay basically just using the built-in tools in Akka.Cluster to do this on our own. We don't necessarily need to go ahead and do custom jobs, but we've worked with some of our customers where they actually probably did need to subscribe to this because they have unique, how do I put this? They have some unique constraints in their domain that require them to do that. Now, the next really cool thing Akka.Cluster can do is heterogeneous clusters. Akka.Cluster would be somewhat limited in its usefulness if all of the code that was deployed on the cluster all had to be from the same code base. Heterogeneous clusters allow us to go ahead and essentially have a cluster that consists of multiple different types of services. That way we can essentially have a hybrid network that uses both peer-to-peer networking and client-server relationships. Which is kind of the best of both worlds. Client-server relationships give us the ability to specialize our code. Peer-to-peer networks give us the ability to have a lot of redundancy and decentralization. So this is from our Akka.Cluster code sample that we use, the web crawler, which is in the Petabridge's GitHub repository. We have, let's say, a couple of ASP.NET and SignalR nodes here that form our web role. They're responsible for interfacing directly with the end user. They join the cluster by talking to Lighthouse. Then we have some crawler roles down here. These crawler roles do all the heavy IO and parsing and basically responsible for trying to build the index. So these crawler roles to work with each other, they talk to each other using Akka.Cluster, and they also go ahead and receive information from the tracker roles. The tracker roles are really our stateful role inside Akka.Cluster. They receive the request to go ahead and crawl a domain, and they're responsible ultimately for building the index and communicating the progress of the crawl back to the web roles. So this is a good example of how to go ahead and use roles to essentially go ahead and segregate our responsibilities across different services. So we have our responsibility for all the heavy IO and parsing here. We have our responsibility for doing all of the UI work. And then we have all our responsibility for doing all the indexing and all the stateful work right here. That's a pretty good set of separation of responsibilities. So Akka.Cluster roles are absolutely essential to the smooth operation of a cluster, in my opinion. So I went ahead and I highlighted the roles definition in HOCON right here. Akka.Cluster roles get used by all sorts of different parts of Akka.NET. Routers use roles to determine which nodes should receive messages. Cluster singletons use roles to determine which nodes can host singletons or which nodes we should contact to communicate with them. Cluster sharding uses Akka.Cluster roles to determine where shards are hosted on the network. Distributed pub sub uses roles to determine who needs to receive events. And then DData uses roles to determine which are the nodes that actually can host replicas and gossip about different types of events that occur behind the scenes. So some roles best practices for you. Every distinct service should have its own role. So if you go ahead and have, let's say, 4 different services, you should have one role for each of those different service types. Now, it's perfectly common, by the way, for multiple services, for each service to have multiple roles potentially. Once upon a time, we actually used roles for communicating version information. We now have a discrete type built into the member class in Akka.Cluster called app version that communicates that now, so we don't really need it anymore. But there's lots of use cases where you might still want to do that. Next, all the nodes that, let's say, participate in distributed pub/sub. This might include many different services that are all using distributed pub/sub to communicate to each other. But there might also be some services like Lighthouse that don't use distributed pub/sub at all. So you should probably have a special role for basically indicating that, yes, I participate in distributed pub/sub. So that should probably use a shared role that multiple services might use. But as like I said down here, don't go nuts. Don't go ahead and define a million different roles. That'll go ahead and complicate your config and potentially your gossip. So you should go ahead and try to limit the number of roles to something reasonable inside your cluster. Finally, anything that can be targeted using a role should be targeted using one. So that means, for instance, even in a homogeneous cluster, you should start using roles from day one and incorporate that into all of your Akka.NET code, because it'll be a lot easier than trying to introduce roles later. This will go ahead and give you a smoother way to transition from a homogeneous cluster to a heterogeneous cluster if you always make sure you use roles from day one. So you should definitely go ahead and do that. All right, now for our last section today, before we get to some questions, I want to talk a little bit about some common tasks with Akka.Cluster. So we've talked a bit about what's the business motivation for using it. We've talked a bit about who's using it and what for. And then we've talked a bit about how Akka.Cluster works. Now let's get to the sort of the more practical stuff, which is how do I do these types of basic common things with Akka.Cluster? So I'm going to define some terms. Work. Work is a task that has to be completed that does not affect entity state. It's a good example. Parsing a document, sending a transactional email to a customer, firing a webhook to a third party, like Slack, for instance, and doing media encoding, or maybe exporting some state to an Excel file or a PDF. Those are all examples of work where they don't really have any effect on a domain, but they are still important because they do things that ultimately are necessary for either communicating with your customers or creating data that might affect entity state down the road. State, in the context of how I'm using it, refers to domain entities from, let's say, a traditional, domain-driven design context. These are the entities that represent important pieces of business data, business objects in the real world. So these might be orders, customers, workflows, payments, transactions, devices on your network, all sorts of things. So that's what we mean when we use the word state. Next, node. A node is a single actor system with a reachable network address that is inside our Akka.NET cluster. So a node can only bind in the context of Akka.Cluster to a single address and is globally, let's say, addressable using that address within the context of the cluster. Finally, a cluster is a network of nodes that have all joined together and formed a peer-to-peer network. And then we have a role, which is a label that describes what types of work a node can perform. So that's kind of the full picture, what we've got so far. So let's talk about distributing work first. So how can we distribute work across Akka.Cluster? How can I receive a request on one node and then farm it out to, let's say, 2 or 3 other nodes inside the cluster? What are my best options for doing that? Well, a couple of different ways of doing it. Actually, I guess I'll offer 3. First is a clustered router. A clustered router uses the exact same routing strategies as normal vanilla Akka.NET. They are very inexpensive. They are extremely fast from a throughput standpoint, and they can be created entirely via configuration. So Akka.Clusters are probably your simplest option for doing that. So we're going to take a look at those in a little bit more detail too. Next is distributed publish subscribe. This requires less awareness of the actor hierarchy design. So I don't necessarily need to know which services have actors at where, because normally if you create a cluster group router, which is what we're going to look at next, I need to know, okay, I want to send messages to nodes with this role with actors in this location on the network. And that basically requires the programmer who's writing, let's say the node sending the message, to know where the receiver lives on the network. That's not a huge deal, but still that can be somewhat inconvenient, particularly if you expect there to be a lot of different receivers of those types of messages. Distributed pub/sub kind of helps compact and compress some of that information by allowing you to go ahead and use simple publish and subscribe relationships to connect producers and consumers together that way. And you can also use groups in distributed pub/sub to create mutually exclusive consumption of messages, meaning that if I go ahead and publish a message to let's say a group, I might be able to say only one consumer in this group should receive this message, rather than having the default behavior, which is that every consumer who is subscribed to that topic receives every message. And finally, we have cluster singletons. Cluster singletons are a somewhat special case. They're really useful for distributing work in a manner that can't really, where the business logic can't really be parallelized. So a good example, resource-aware work distribution. This happens a lot in those types of, let's say, batch computing scenarios quite a bit. And then, or running work on a clock. So where you have, let's say, a scheduler or in a scheduled job you need to run, that's not a type of workload you can really easily parallelize. The actual processing of those jobs can be parallelized, but not owning the schedule. You probably want a cluster singleton for doing that. So this is what a clustered group router looks like. Node number one is going to create, let's say, a round robin router. And it's going to say, I want all the nodes of role type X to basically add a recipient at this location in the actor hierarchy. So by the way, nodes 4, 3, and 2 have already created this actor. This actor is just being pointed to by this router. And so every time I send a message to this router, depending on how that router is configured, it'll either send that message to every recipient or just a single recipient. And that really depends on the HOCON configuration we use there. So that's a really simple tool for being able to distribute work. If node number 4 became unreachable, then node number 1 would only route those messages to node 2 or node 3. So we have the ability to go ahead and essentially filter out those unreachable nodes until they become reachable again. And this is what the HOCON looks like for going and setting up a cluster group router. So you can, by the way, anything you can do in HOCON, you can do in C# for configuring specific actors. One setting we typically don't use very much with a cluster group router is this number of instances setting. You don't need to specify it. And if you do specify it, you might unintentionally limit the number of recipients who can actually receive messages from a router. So that can be a bit of a problem. But I'm going to go ahead and create a broadcast group router here, which means every recipient receives every message. I'm going to say the recipients are going to live on this location inside the actor hierarchy of the nodes who can receive this message. And I'm going to specify that those actors have to go ahead and live on an actor system that has a role of type crawler down there. So that's what that means down there. All right, so that's cluster group router HOCON. Next, let's talk a bit about distributed pub/sub. So distributed pub/sub works through this plugin here, the distributed pub/sub plugin. It's part of the Akka.Cluster Tools NuGet package. And you get a reference to a special actor called a mediator right here. This mediator, you have to go ahead and tell it that I want to subscribe myself to this topic. And topics are all strings in distributed pub/sub. I'm going to get a receive act back when I have successfully subscribed to that topic. Well, if anyone else wants to publish a message to that topic, they just need to tell that mediator actor, I want to publish to this topic and I want to send this message. And that message will get serialized and then transmitted over Akka.remote, and I'll eventually receive a copy of it right here. So distributed pub/sub is fairly transparent. It doesn't take a huge amount of code to wire into it. This is how it actually works behind the scenes though. So if I have an actor down here that's going to publish a message, and I say, I want to publish message T to topic foo. What's going to happen is the mediator running on the local node where I publish it is going to first publish it to all of my local subscribers. That's all going to be done in memory. And then I'm going to go ahead and compute which of the other mediators running inside Akka.Cluster have at least one subscriber for topic foo. And for every mediator that has at least one subscriber, it's going to receive its own copy of this message. And here's the really cool part. Distributed pub sub is traffic optimized, where if I have, let's say, 1,000 subscribers to this topic running on this node, I only have to send one message over the network. After that message is deserialized and handed over to the mediator, it's going to go ahead and distribute an in-memory copy to each of these subscribers. That way, we're not producing a huge amount of serialization and networking overhead for each of these publish operations. So we're able to really compress the amount of network messaging that has to go on behind the scenes for all of these different topics that are published inside distributed pub sub. So that's kind of the basis of distributed pub sub. Now, I'm going through all these pretty quickly. This isn't meant to necessarily be an in-depth tutorial on all this stuff. What I'm just trying to do is present you with the set of options you have for working with Akka.Cluster and make you aware of what tools are useful under what situations and kind of roughly how they work. That's all I'm trying to accomplish here. Now, next, Akka.Cluster Tools Singleton. This is probably the most interesting of all the different workload distribution tools because it's basically a way of guaranteeing there is at most a single copy of an actor inside a cluster at any given time. And this is really useful for different types of workloads that can't be parallelized. So schedulers and job trackers are good examples of this. So if you're trying to run, let's say, a bunch of really expensive batch jobs, and you want to try to maintain maximum throughput, which means not letting some jobs start until other jobs finish. Otherwise, everyone's competing for the same resources. Having a job tracker that uses an Akka.Cluster singleton for keeping track of where jobs have been allocated is a really effective way of doing that. By the way, Akka.Cluster singletons almost always are persistent actors. They tend to persist their state and recover it when they move. That's just, those two just happen to kind of show up together quite a bit. So this is how we might instantiate a singleton actor. We go ahead and we call actor system to actor of cluster singleton manager.props. And then we pass in the props of your user-defined actor that you create is what gets passed in there. And then we go and we pass in some settings here. We say, okay, this singleton can only live inside, let's say, the pricing engine role. And it's going to have a name called price initiator. And they're going to give this actor a name on the actor hierarchy right here. In order to talk with the cluster singleton, if I want to send it messages, I have to create what's called a cluster singleton proxy down here. And I'm going to say, all right, I'll grab my little laser pointer, that this singleton is going to live basically on whichever node it's hosted on. It's going to be found on this location in the actor hierarchy. And I'm going to go ahead and say, okay, actually, I should have changed this name on here. These two, well, actually, I guess these are two different actor systems. That's why this works. But my cluster singleton proxy settings.create, I'm going to say you need to talk to a pricing engine node in order to basically find this proxy. And so let me go ahead and get rid of my laser pointer here. If you want to see how this works, node number 4 is trying to talk to one of the singletons that's hosted on, let's say this is a different role type than these three. Well, right now we're talking to the oldest node in the cluster. And by the way, cluster singletons automatically gravitate towards the oldest node of that role type because it assumes that node is part of the minimum viable set of nodes there. So if you're doing auto scaling up and down, the newer nodes are probably also going to be the first nodes that get removed when things scale back down again. So we're trying to avoid that. So we're going to go ahead and try to always park our singletons on the oldest possible nodes. That way we don't have to move them in the event that auto scaling happens behind the scenes. So the singleton proxy is going to point to the current singleton. And then when this node becomes unreachable, it might eventually get kicked out of the cluster by the split brain resolver that runs inside our cluster. Well, what's going to happen is node number 2 is now the oldest node. And we're going to go ahead and point to the singleton, and the singleton is going to be recreated on this node. And the singleton proxy will go ahead and start pointing towards this actor instead of the previous one. So that's a little bit about Akka.Cluster singletons in a nutshell. So that's all about distributing work. In terms of distributing state, as a rule of thumb, all state, basically any stateful domain entity should be hosted inside its own actor. That allows us to go ahead and parallelize, updating multiple entities concurrently. It also allows us to distribute entities evenly across an arbitrarily large number of nodes inside our network. So Akka.Cluster Sharding is probably the best tool for this. because it guarantees structurally at most one copy of an entity can exist at any given time. And that's even true across network partitions. We're able to guarantee that. Entities are always evenly distributed amongst nodes, and redistribution occurs in a safe manner inside Akka.Cluster Sharding. And I'll show you what that means in a moment. And then entities can also be passivated when not used, which means that if this entity hasn't received a message in a while, we're going to automatically shut that actor down and then recreate it on the fly. The next time someone sends a message, address that entity down the road. So that actor is theoretically immortal, but it's going to go ahead and be shut down and recreated as a result of, let's say, inactivity will cause the shutdown, or when messages are sent. We do have a setting in cluster sharding called remember entities, which changes this behavior. It means that entity is always active, regardless of what message traffic it's receiving. And that can have a little bit of impact when you're rebalancing shards in a cluster. That can have an impact on how many entities have to be restarted all at once. The other tool we have for distributing state is consistent hash routers, which use a similar type of math for guaranteeing a unique distribution of entities, but they're dangerous. The reason why is consistent hash routers don't really have a built-in way of reasoning about moving partitions from one node to another. So that might mean you might have two copies of the same entity that both think they own the source of truth for that state. That is somewhat dangerous. Cluster sharding is the right way to go ahead and work around that problem. So that might be something you might want to take a look at if you're evaluating Akka.Cluster for your project. Now, the way cluster sharding works is we have to create what's called a shard region. Think of this as the aggregate root. If you're a domain-driven design practitioner, this is the aggregate root for a set of all possible business entities. This aggregate root is going to create shards, which are basically a bounded context, and it's an arbitrary bounded context that's going to group a set of entities together. By default, most shards are determined using consistent hashing, where basically we're going to have, let's say, 30 shards, and they're going to own an arbitrarily large number of entities. And all the shards, all the entities that fall inside the same part of the hash range will all be assigned to the same shard, meaning that those entities don't have any relationship to each other. You can write custom sharding, let's say sharding message extractors, which can group entities together in different ways too. So for instance, if you're building, let's say, a sports betting system with Akka.Cluster Sharding, you might have some shards that go ahead and group, let's say, entities that all relate to the same team together. That way, if those entities all need to send each other messages, they can do that all in memory inside the same machine. And you can avoid additional network IO that way. And these are all the entities right here. So what's going to happen is that as messages are sent to the shard region actor, we're going to see that actor in a moment, I think, we'll go ahead and dynamically allocate shards, and the number of shards is going to be specified in your message extractor. And then we'll go ahead and automatically instantiate entities inside that shard. And these shards are the unit of work that can be redistributed if the cluster gets too heavily loaded on a small number of nodes. We're always trying to maintain, for availability and throughput purposes, a relatively even distribution of shards throughout the cluster. This piece of code right here is the message extractor. It's going to determine how many total shards we can have. And this bit of code is going to run for every single message that gets sent through the sharding system. We're going to go ahead, in this case, this is from our Akka.Cluster workshop. We're going to go ahead and inspect this little interface that might be on that message we're sending, this I with stock ID. And we're going to extract the ticker symbol, and we're going to use that to uniquely identify this entity inside our system. So all messages that belong to the same entity all get routed to the same actor. That's what this entity ID has to do. It's like the natural key for this entity. So in your domain, that entity ID might be the unique identifier of a user, the unique identifier of a transaction, the unique identifier of a device in your network, any number of different things. That's really what we're trying to do here. We're trying to tell the cluster sharding system, how do you differentiate one entity from another? That's what that's all about. So the hash code message router is going to use consistent hashing to go ahead and figure out how to group entities together inside of shards. And the rule of thumb we're going to try to use is that for the number of nodes that are capable of hosting shards, we're going to go ahead and take that number and multiply it by 10. That should give us a relative. So let's say if I have 5 nodes that can host shards typically, that means I want to go ahead and have a shard count of 50. That'll help us achieve a nice balance between making sure our shards, in the event that they get rebalanced as the cluster scales up and down, that we don't impact a disproportionately large number of entities at any given time. But it also means that we're not also constantly rebalancing either. This is kind of like a happy medium in terms of the total number of shards. And this is how we actually go and start the sharding system here. This is the Akka.Cluster Sharding plugin. I call get on the actor system, and then I call sharding.start, and I name the type of entity we're going to use. So this is just a string right here. So this might be, orders, customers, products. And then I create what's called entity props. And these entity props are basically, it's a function that's going to go ahead and create props for a new entity actor. So each entity gets its own actor. Or we can go ahead and just pass in the props directly right here. I prefer the function syntax where the input is a string that represents the entity ID, and the output is props. I tend to prefer using that syntax. This is using the older syntax though, this little example. And then we pass in our message extractor, that piece of code you saw me create a little bit earlier. That's going to figure out how to go ahead and separate from each of these shard regions. This shard region, by the way, this is an actor reference, this piece of code right here. We basically send messages to the sharding system by telling messages to the shard region actor right here. And so shard information gets replicated throughout all the nodes that are capable of hosting shards. So if I go ahead and have, let's say 9 shards here, and these are all, let's say, this is for a different shard region down here, but these shards are both for the same order, for the same type of entity and order book. What's going to end up happening is we're going to go ahead and have our sharding coordinator, which, while this is using like the old model, which is Akka.Persistence, the new model is there's actually a coordinator that lives on each one of these nodes. And what's going to happen is when I send a message to the shard region, that message is going to get transmitted from, let's say if I send a message to the shard region actor on node 1, and that message gets computed as belonging to an entity that is a child of shard number 7. Well, I know based on the data that my coordinator has that shard number 7 belongs to node number 3. Therefore, that message will be serialized and routed over the network and then delivered to the appropriate entity actor here. So it gives me a location transparent way of being able to distribute my entities in a even fashion. It gives me the guarantee that there will be at most 1 copy of that entity inside the cluster at any given time. And it also gives me the ability to safely and securely hand over partitions as my cluster scales up and down. We also have a tool similar to the cluster singleton proxy called a shard region proxy that allows a node that's not capable of hosting entity actors to still communicate with them. And that's what this little bit of diagram kind of illustrates right here, which is that in the event that let's say I want to go ahead and try to find, let's say, an entity that lives somewhere on this node, the shard region proxy will receive a set of updates from the coordinator, and it'll go ahead and say, okay, I know that this entity lives at shard number 3. So I'll be able to go ahead and send it messages that way. And it'll go ahead and dynamically kind of construct a route for being able to send messages to those actors. Lastly, I kind of want to illustrate shard rebalancing. When a new node joins the cluster, let's say node number 3, it's going to start up a shard region. Well, that shard region has no data inside of it. So the sharding system is going to gradually move some shards from the older nodes and redistribute them inside node number 3. That way we maintain an even distribution of shards across all of our nodes. So that's one of the things that cluster sharding will also do for us. So let's try to maintain a relatively even distribution of state inside our system. Let's see now, the last thing we're going to go ahead and cover today, we're going to cover distributed data and then a couple of quick slides on best practices for smooth operation and deployment of a cluster. Distributed data is one of the newest parts of Akka.Cluster, and it's a fairly advanced feature that most end users probably will never need to use. It gets used indirectly behind the scenes by Akka.Cluster Sharding. It allows us to create in-memory, replicated, eventually consistent data structures, which means that you can have a copy of this entity that lives concurrently in like 3 places inside your cluster. All 3 of those copies can be modified and merged together back into one consistent view of the data. And it's able to accomplish this using a specialized data structure called a CRDT, a conflict-free replicated data type. And this allows us to immutably update state across multiple nodes. Most apps don't need it unless you want to go ahead and have really high availability for important objects in multiple locations. So if you're building something like, let's say, a foreign currency trading platform, and you need to maintain a live, let's say, cache of all the different exchange rates and different providers, that might be something you'd stick in DData. Or you want to avoid persisting every change for rapidly updating objects, but you still want some redundancy in case a node goes down. Akka.Cluster.DistributedData can help offer that to you. Now, we still have the ability to support these CRDTs through an additional NuGet package called Akka.Cluster.DistributedData.LightningDB. This goes and uses the local file system of each node to go ahead and persist these CRDTs in a serialized format. And we're in the process of making some additional updates to that right now. But that's fully supported too, is being able to go ahead and have persistent copies of the CRDTs. So what this looks like in practice is each one of these nodes might be running Akka.DistributedData. If I go ahead and say, I want to update an OR set, an observe remove set, it's like a hash set to one of these CRDTs with a specific key. I want to go ahead and add an item to that hash set. Well, what this is going to do, I can go ahead and basically specify when I update the CRDT, what level of consistency do I want? Do I want to go ahead and do a full quorum write, which means that every replica has to acknowledge the write all at the same time? Well, if they do, I'm going to go ahead and when I write this to my local replicator, it's going to go ahead and also push that update to these other replicators here, and they're all going to send an acknowledgement back. And the write will complete with a successful status if everybody acknowledged it. Now, if the write didn't complete successfully, guess what? Some of these replicas probably already have that update, but CRDTs are idempotent, which means you can retry doing the update again, and you won't have any duplicates or anything like that. CRDTs are fairly robust in terms of being able to handle those types of updates. And then finally, if I'm subscribed to changes for a specific, let's say, distributed object, I'll go ahead and receive the delta, basically the incremental change that was made to that OR set. I'll go ahead and receive a delta for that once it's been replicated to my local copy here. So CRDTs are pretty useful for being able to perform this type of, let's say, distributed in-memory replication. And the way this looks from a source code perspective is I'm going to go ahead and create a little replicator right here. And I'm going to go ahead and basically just call actor of replicator right here. I'm going to go ahead and tell the replicator that I want to subscribe to these different keys. These are little key objects that are built using the DData domain-specific language. And this is an actor reference right here. I'm going to tell that I want to go ahead and try to read my local copy of this distributed object. And I expect to find a not found object yet because no one's actually tried to create the CRDT. But down here, I can go ahead and say I want to create a new G counter. This is a counter data type that's replicated. I'm going to go ahead and say I want to go ahead and increment it with a value of 3. Well, I'm going to go ahead and create an update for this empty G counter right here for this key. And I'm going to use this little function to specify how I want to try to update that. And I'm going to specify that my write consistency is going to be local, meaning I'm not going to go ahead and wait for every other node in the cluster to receive a copy of that. I want to receive a notification once I know that my local state's been updated. And when that happens, I'll go ahead and receive an update success down here. So that's distributed data. That's probably one of the more advanced ways of trying to go ahead and distribute state throughout an Akka.NET cluster. Most applications don't need it, but you can do things like build, let's say, distributed order books, or maybe, let's say, distributing cached objects. You can do all those sorts of things fairly cleverly using distributed data if you want. Now, last thing I kind of want to finish with before I get to all these questions. I see we've got about 24 questions so far in Q&A. Before I get to those, the last couple of things I want to touch on: designing effective Akka.NET clusters. Well, first, you want to separate stateful work from stateless work. Stateless work doesn't have side effects, which means that it's very safe to go ahead and retry failed, let's say, stateless operations somewhere else inside the cluster. So that's one important reason for keeping them separate. You also want to keep them separate for noisy neighbor reasons. Stateless work often tends to involve things like I/O or document export or that type of thing. You don't want the overhead of that interfering with your ability to get access to your business state. So stateful work, if it has to be retried, comes with cap theorem consequences, meaning you have to worry about the consistency with how that retry is done, depending on how you've modeled your state potentially. A system like CRDTs eliminates a lot of that, but comes at the cost of eventual consistency. So retries are cheap in distributed data, but the rate at which those changes get propagated over the network is slower than, let's say, a system like SQL Server, for instance, which is a strongly consistent type system. You want to run as little stateful work as possible. If an operation inside your cluster does not need to be modeled statefully, then it probably shouldn't be modeled statefully. The reason why is that stateful work requires you to have a way of migrating state from one location to another. We saw Akka.Cluster Sharding rebalancing, for instance. That's one example of an approach for migrating state from point A to point B. Moving replicas around in distributed data is another way of doing that. That can be expensive potentially. So you want to try to have as little of that as possible. So CRUD can be okay in a whole bunch of different areas of Akka.net. So for instance, one area where I might use CRUD inside SDK bin is maintaining an index of all the different entities of a certain type inside my system. That's fine being CRUD because occasionally I need to do an index scan. And that's not an operation that's going to happen at super frequent rates. But when it does happen, having it sitting there inside a SQL table is pretty inexpensive at the end of the day. Now, as far as actually rehydrating the state of all my entities and processing a workflow on them, I'd rather have that run as a stateful workflow inside an actor. So I'll use state there, but not necessarily the index of all the actors that have the process work at any given time. I might stick that back in SQL Server. So run as little stateful work as possible. For things that do need to be stateful, absolutely. Akka.Cluster Sharding is probably the right way to go there. But if you can get away without modeling it that way, then you should try not to. Finally, domain entities, just use cluster sharding. Don't try to reinvent the wheel on that. Cluster sharding has solved a lot of hard problems around doing state handoffs, being able to maintain even distributions of entities, being able to go ahead and make sure that entities are shut down when they're not being used and recreated on the fly. I would not recommend trying to compete with that. It's a lot of work. You'll be a lot better off just using cluster sharding. And then lastly, a couple of important things for operation and deployment of clusters. I'm doing this, by the way, with an eye on services that are trying to maintain very high amounts of uptime. In order to even theoretically achieve 100% uptime, which probably isn't possible for most services, inevitably you're going to have some problems at some point in the future. But in order to try to maintain 100% uptime, you have to very carefully version messages and services. The best way to do this is to embrace a practice which we are covering in our, we cover this in our remoting course for Akka.net, but we're also going to be covering this in our Akka.Cluster workshop that we're going to be putting online. Extend-only design is the best way to do it, meaning you never go back and ever change the meaning of anything that's already in service. So to use a SQL term, alter statements are banned, basically. Never, the only way, let me rephrase that. Alter statements that mutate an existing column are banned. Alter statements that add a new column are fine. You can go ahead and do that. So extend-only design gives you a sort of a sane approach for being able to version it and extend events or introduce new ones if you want. And then couple this with a schema-based serialization approach, such as Google protocol buffers. You'll definitely be better served over the long run doing that. Using reflection-based magic and that type of thing for doing serialization of messages and of your persistent, let's say, formats, that will always eventually come back to bite you. It's a matter of when, not if. A schema-based approach, though, puts you in charge of how those are managed. Even though it takes a little bit more time and effort to set up initially, it will pay for itself 1,000,000 times over the course of a very long-lived service, I promise. Next, minimize the number of types needed to represent discrete events. Not every single event that happens inside your system should necessarily have its own type. And the reason why you want to try to avoid that is because you're responsible for kind of maintaining how these types are represented on the wire. And that can actually be quite expensive if you allow there to be a huge number of them. Maintaining 2,000 different, let's say, message definitions and trying to version those sanely is a lot harder than maintaining 12. So you want to go ahead and be responsible about that. One thing I tend to do is I tend to separate types that can go over the network from types that can't. And I can go ahead and actually assert that inside the Akka.NET testing system by using serialization flags. The serialized messages equals on sort of settings. I actually don't want messages that shouldn't be going over the network to be serializable necessarily. I want those to fail. That way I know they're not being leaked where they shouldn't. As I say down here, if you're trying to minimize the number of types that can go over the wire, the way to represent multiple discrete types of events is through the type's content, not through the type's type. That's how to do it. Lastly, stateful nodes require different types of deployment. You never want to do a VIP swap, which is how we've been used to deploying things like, let's say, web applications for a long period of time. That will come back to haunt you. You don't want to do that. That'll create split brains and all sorts of other problems. What you want to do instead is replace nodes one at a time. We tend to do here at Petabridge like a little, I guess I call it a canary deployment, where we go ahead and we pull out one node and replace it. And if that node doesn't, and we automate this through Azure DevOps and Pulumi, but if that node doesn't successfully start up, the rest of the deployment just gets halted until a human can go in and take a look at it. That's worked pretty well for us over the past year or so. For SDK bin in particular. And that's what I tend to see a lot of our customers do as well. So that's probably the right way to go ahead and deploy stateful nodes. So stateful nodes need to be handled with a little bit of care. Next. Generally, better to deploy services independently from each other. So one of the kind of problems we have with SDK bin right now is when we rapidly developed it, we did it all as a mono repo. So everything gets deployed at the same time. Those deployments tend to exert a lot more strain on the cluster than just deploying, let's say, deploying a single service at a time. So I would recommend trying to go ahead and make it so your deployments are more granular. That'll make it less impactful in the cluster. It'll make it kind of easier to do things in isolation. And on top of that, in the event that something goes wrong, rollbacks are a lot easier to execute in that type of environment. So that's another thing I recommend doing. Now, that kind of marks the end of our presentation today, and I'm going to take some questions. But if you're interested in taking a look at clustering for your company, a couple of things you should take a look at. One is that we have some upcoming trainings, I believe, not next week, but the week after, for covering Akka.NET design patterns and remoting. So those are multi-tenant trainings. It's free for, not free, excuse me. It's anyone is welcome to go ahead and sign up. They cost about $500 per seat. So those are coming up starting, I believe, on July. Look at my calendar here. Let's see. That should be starting on July 12th is when those are coming up. So that's one thing you might want to take a look at. Next is we do offer in-person. We're all fully vaccinated here. We do offer in-person and online group trainings. So we've been doing recently a lot more online group trainings. That's something you can schedule for your company. These are a good choice if you want to train, let's say, up to 10 people at a time. We do this on your schedule and in your time zone as well. And finally, we gave a little webinar on this back in late January. We also have Phobos, which is a great APM tool for being able to go ahead and visualize how things work inside your cluster. So these are a couple of other options for you to consider. Now, without any further ado, just check the time here. Let's go ahead and take a look at our Q&A. Okay, so I'm going to go ahead and start at the top here. All right. Can we have Docker compose.yaml file for an Akka.remote deployment? We do have some examples of this inside our cluster.web crawler repository. That's going to be a Docker compose deployment that uses Akka.Cluster, and that does use some remote deployment where actors are being deployed from one service onto another. Let's see. Next question. Persistence equals event sourcing. Yes, Akka.persistence uses event sourcing under the covers. All of the events that are saved using those persist calls are all basically saved to a little append only log behind the scenes. So that's kind of what's going on underneath the covers there. We also support the ability to do projections and snapshots, which are other important properties of event sourcing. And so a snapshot, you can just save individually inside one actor. For doing projections, we have an additional library called Akka.Persistence Query, which most plugins support. These allow you to go ahead and query events from the journal and remix them and replay them in whatever order you want. Let's see. Is it mandatory to use Lighthouse as a seed node in Akka.Cluster? Absolutely not. Lighthouse was just something I created because I needed it 8 or 9 years ago, and it well, 7 or 8 years ago. And so no, you definitely don't need it. There's nothing special about Lighthouse. It's just headless Akka.Cluster. Can we use our own API as a seed node in Akka.Cluster? Yes, you can. You can absolutely do that. You can go ahead and basically just specify that in your little seed node configuration. All right. Would you recommend to use Kubernetes in combination with Akka.Cluster? It seems there are many interaction of features among both technologies. Absolutely, I strongly recommend using Kubernetes for managing Akka.Cluster because Kubernetes has built-in support for being able to go and deploy stateful services, which most other environments do not. So that is a very useful tool. On top of that, Kubernetes also helps quite a bit with networking and service discovery in Akka.Cluster. So those two technologies complement each other pretty well. We personally use Kubernetes with Azure Kubernetes Service for SDK bin here at Petabridge. And our Akka.Cluster workshop, which we're in the middle of updating it right now. But when we go ahead and we publish that, that is all about using Kubernetes with Akka.Cluster. And that course is very similar to Akka.NET Bootcamp. It's a free learn by doing course. And we'll go ahead and publish that probably the next couple of months here. Is Akka.Persistence distributed as well? Akka.Persistence is localized per node typically, where all the code runs using a journal that's local to that actor system. However, because all of those actors are all talking to the same database, it theoretically can be distributed. But most importantly, you want to make sure that no two actors in the same network talking to the same database have the same persistence ID. Otherwise, that'll cause the data for both entities to be corrupted. So that's what Akka.Cluster Sharding is there to guarantee. It's there to guarantee that at most, one copy of an entity exists anywhere inside the cluster at any given time. And that's able to go ahead and preserve that sort of uniqueness guarantee that Akka.Persistence depends upon. If you have a persistent actor, let's say a people actor, that is running inside a cluster, will there ever only be one instance that represents people/user A and only one instance for people/user B? That's what Akka.Cluster Sharding does, where this user A setting would go ahead and be determined by the Akka.Cluster, Akka.Cluster Sharding entity ID. Okay. If not, what happens to the persistent data on the node if it dies and another node should take over its work? How does it get the current state? What will happen is any of the data that was successfully persisted, Jose Silva on YouTube is asking, where am I reading the questions? It's from Zoom, is where I'm reading that data from. But I'll answer, don't worry, Jose, I'll answer your questions too. But what I was gonna say is that data is good. Oh, sorry. That data will go ahead and be recovered by another actor that starts with the same persistence ID. It'll go ahead and query the journal, which is backed up to a database. And it'll go ahead and replay that, deserialize all those events and use that to rebuild its state. And then once that's done, the actor can go ahead and resume processing messages as normal. Can I expand on how nodes discover themselves? What will happen at startup is nodes will go ahead and read their Akka.Cluster.seed nodes configuration, and the seed nodes will go ahead and join each other. They'll go ahead and form a network together. Any other nodes that start will need to be configured with at least one of those seed nodes addresses in its own seed nodes field. When it establishes a connection to one of those seed nodes, it'll receive a set of gossip data that has all of the addresses for all the other nodes inside the cluster there. And we can go ahead and use that to go ahead and start the process of forming our topology together. Are there any tools that allow us to visualize the Akka.Cluster network topology and the node's health? Phobos will allow you to do that. Petabridge.command will also allow you to do that. It'll go ahead and give you a printout of what the current state of the cluster looks like, and it will allow you to go ahead and subscribe to changes in the cluster topology. Okay. Can I give you a quick comparison of Akka.NET, Project Orleans, and Protoactor? So I would say that the biggest sort of differences Akka.net is highly versatile, can be used in a lot of environments. So for instance, we have some questions in the YouTube channel about can Akka.net be used for MVVM? It absolutely can. Akka.net can be embedded directly inside the client UI on mobile or desktop applications. And in fact, we actually have a pretty large community of Unity 3D users who use Akka.net behind the scenes, as well as some people who use Akka.net in environments like Xamarin. So Akka.net is designed to basically scale all the way down to running in a local environment, but it can also run as a large distributed system. And one of the, I think the biggest differences between Akka.net and Orleans is that Orleans is all about distributed systems. But Orleans is basically kind of all built around what cluster sharding does. This idea of these immortal sort of entity actors that you can basically go ahead and query via a unique identifier and recreate on the fly. Akka.Cluster Sharding works much the same way, but it also has the ability to work in a whole bunch of different modes too, where you can have some actors that aren't immortal entities. They might be somewhat transient actors or utility actors that manage a pool of resources and that sort of thing. I would say the biggest difference is probably that Akka.net kind of has a lot more of an upfront learning curve in terms of the different types of things you need to learn in order to work with it effectively. Whereas Orleans is kind of that Microsoft style magic project that papers over a lot of that, kind of like how Entity Framework does for your ORM, in order to get you up and running more quickly. And ultimately at scale, you do have to learn how those abstractions work in order to leverage them effectively. So it's just kind of a matter of when you pay for it, not if you're going to pay for it. As for ProtoActor, I don't really know much about them. I think they are basically kind of a virtual actor model similar to Orleans. So the distribution system is pretty similar. They were meant to be cross-language, if I recall correctly, where actors in Go can talk with actors in .NET. But otherwise, I haven't really paid much attention to it. They don't have much in the way of documentation or really material for me to take a look at. So I don't really know what's the most recent story over there. Okay, Gustavo, how ActorSystem.create is using the same ActorSystem name in each microservice.web API. Can I actually do something like, okay, let me just parse this real fast. Okay. Okay, so basically, how can I go ahead and, so since each node in an Akka.NET cluster is running with the same actor system name, how do I go ahead and know basically, like say, if I create a router, how do I know that router isn't created on all the other same actor system names? Well, the reason why is because, like I mentioned earlier, when I call that actor ref method, that actor is only created locally by default. So any other different, let's say, any other actor systems that are waiting to go ahead and receive messages all have to create their own copy of that router. So a clustered router is able to receive that gossip data to add routees, but that router itself is local to the actor system that created it. That's why it's okay to go ahead and have each node create its own. Wow, I keep trying to go through these questions, but the more and more of them keep coming in. Okay. We will be migrating a custom sharding solution of an existing Akka.NET over RabbitMQ to Akka.Cluster. Okay, so they have a current solution that's using Akka.NET on top of RabbitMQ. They're moving it all to a sort of a dedicated Akka.Cluster system. Are there any shareable performance metrics for Akka.Cluster in order to better assess our migration results? You know what? I'm going to pull up, I'm just doing this on another window here, and I'll bring it over. But we actually do have a project here that we created pretty recently. I'll go ahead and actually, you know what? I can't quite share it on screen, so I'll drop it in chat because of the way my screen sharing is set up. We have a project called, go and drop a link to this here, Akka.NET integration tests, which will run a distributed benchmark with an arbitrary number of nodes in Akka.Cluster that can help you kind of measure the total end-to-end performance. And this is using a bunch of rapid ping pongs back and forth. That's one way you can kind of establish a performance baseline in your hardware and in your environment. And by the way, that test also supports Docker if you want to run it inside of there. But in terms of what performance you should expect, it'll kind of depend on what you're persisting. It'll depend on what the sort of, let's say, round trip communication time looks like. Right now, over a single Akka.remote communication, I'm running a Generation 1 Ryzen machine right here. I can do about 200,000 messages per second over a single connection. Over, let's say, a dozen connections, I'd probably be able to do about, on a per connection basis, I'd probably be able to do about 100,000 messages per connection, which would give me a total end-to-end throughput of about 1.2 million right there. So it kind of varies a little bit by workload. So you'll want to go ahead and take a look at sort of what the total end-to-end processing time for each individual entity actor is. We're always continuously trying to beat overhead out of Akka.remote in order to make it faster and faster. And Akka.net 1.21, the most recent, or see, 1.421, excuse me. The most recent version is a significant performance improvement over 1.420. What is a sensible size for a cluster in terms of P2P connections established? I would say the average cluster size I've seen in production is probably around 50 nodes. If you have a cluster that's running, let's say around 250 nodes, that should be fine as well. Once you start getting into the ballpark of, let's say, 400 or 500 connections, that's going to be pretty big. Let's see. Aaron, we cannot see the metrics project. Oh, yeah, no, sorry about that. I went ahead and just dropped a link to it because Zoom is basically programmed right now only to look at my GoToWebinar, or so only look at my PowerPoint. Sorry about that. I'm not sharing my entire screen, just PowerPoint. Although maybe I can go ahead and change that real quick. Yeah, okay, let me give this a try. Okay, that worked. All right, this is my set of Akka.net integration tests right here. So you should be able to go ahead and see all of the different, oops, let me get that out of the way. Okay, hopefully that's working now. All right, perfect. Yeah, it looks like it is good. I just had to double check the YouTube feed. This is the Akka.net integration test project. You can go ahead and see down here, like we basically have a bunch of different tests for, let's say, measuring things like Akka.net persistent throughput. If you want to go ahead and measure how quickly you want to go ahead and do an Akka.Cluster benchmark, the Akka.Cluster ping pong project right here is the one that you probably want to execute. So we have some details on how to run that. I've run this locally on my own hardware here. I've run it inside Docker Compose. I've also run it inside Kubernetes. So these are some of the things you can go and take a look at for trying to scale that up and down. All right, let me pull the PowerPoint back up. Q&A. Answer live. Is Akka.net faster than a single-threaded application? If you can model your entire application using just a single thread, that will almost always be faster than a multi-threaded one, just because you don't have any context for overhead switching there. But as soon as you need parallelization to be able to go ahead and actually, let's say, achieve a sensible amount of throughput, Akka.net is definitely a fairly robust way of doing that. So if you're, let's say, just to rephrase that, let's say if all your code can be modeled just inside of a for loop or a while loop, that's going to execute a lot faster than, you know, sending a whole bunch of messages to an Akka.net actor. There's the overhead of actually dispatching that asynchronously to the actor is going to be greater than the cost of iterating through that loop. But if you need to execute, let's say, a whole bunch of asynchronous IO operations you want to run in parallel, or maybe even some asynchronous compute bound operations, parallelizing that across multiple cores, and then Akka.net's going to offer you higher throughput than doing it all on a single thread. Can you explain again how the first node is configured as the leader? Yes, sure. We use a leader election algorithm in Akka.Cluster known as the bully algorithm, which basically means all of the addresses that Akka.net uses for identifying nodes in a cluster, they implement the I-comparable interface. The node that is reachable, that is at the top of that sort order, is the leader at any given time. When a network split happens, let's say the cluster gets split in half, there's going to be two leaders. And that's why you might want to use a split brain resolver algorithm, which is something that we have pretty well documented on the Akka.net website. That'll go ahead and basically have the leader that's in the minority side of the cluster usually shuttle those nodes down. The leader of the majority side of the cluster will kick those other nodes out. That way you end up with one contiguous cluster afterwards, and that should help you maintain a degree of data consistency when you do that. Is gossip something that can be controlled via code? You can go ahead and have nodes join and leave the cluster via code, which is what produces gossip. You can also change via configuration the gossip interval if you want, but you can't necessarily programmatically control when gossip is sent. When must we use Lighthouse? Never. Lighthouse is something that you only should use it if it's convenient. It's something that I use basically if I just want to have a set of static seed nodes that never get touched during deployments. That's something that I tend to do. Should each entity be an actor? Yes, it should. And entities should always be their own actors so they can be parallelized and they can be distributed across the cluster. Can you address the delivery guarantees and messages in a cluster? Absolutely. Akka.Cluster by default does not guarantee any delivery. We use what's called at most once delivery, and we use that because it's low cost. There's basically no state needed to keep track of the delivery of messages. That being said, Akka.Cluster.Sharding does maintain an internal buffer of messages that are going to be routed to entity nodes. And when it knows those entity nodes are in the process of being moved around the cluster, it'll go ahead and close the tap, buffer those messages, and then redeliver everything in that buffer once those entities have been rehomed onto a new node inside the cluster. So other than that, there are no delivery guarantees inside the cluster. You'll want to use something like the Akka.Persistence at least once delivery actor to help retry delivery of, let's say, messages. Or you might want to use a pull-based model like Akka streams, like stream references can help you do that. Or maybe something like Apache Kafka. We're going to look at using stream references inside SDK bin, mostly because we actually added Kafka to our cluster, and it's the way we're using Kafka on top of Azure Event Hubs, and that service has been a source of a lot of errors in our log just because those Kafka clients get shut down mysteriously all the time on their own. So we're probably going to move to an Akka streams-based pull model to replace Kafka instead in those areas there. Now, if we were running our own Kafka cluster, that'd be a different story. But it's because the Event Hub stuff appears to be shutting things down behind the scenes. That creates a little bit of a problem for us. Okay, Malcolm Lerner. If one system has a sort of let me answer this live. If one system has a sort of read-only service, meaning no writes to data persistence, that streams event data using Akka.Persistence query in order to retrieve data, is there a benefit to making that read-only actor system part of the cluster that also includes the right-side actor systems, or is connecting to the data store generally sufficient? Connecting to just the data store directly should be fine. The only reason why you might want to have it inside the same cluster would be if you wanted to subscribe to availability changes for those nodes. Like if you know, for instance, that, well, I don't know, one of those nodes has become unavailable, and that means that your views aren't going to be updated for a few moments. That could be useful, but that's a fairly trivial kind of edge case, to be honest. Otherwise, I think Akka.Persistence query is probably sufficient for that. I wouldn't bother integrating them in the cluster if I didn't have to. Okay, all right. Let's see, next question. Is there a best practice for communicating to a sharded cluster, i.e. via inter-role communications versus a cluster? I think you mean a shard region proxy. I would almost always use a shard region proxy because it can tap into the buffering system that I mentioned just a minute ago. They also will use buffers when entity actors are being redistributed. So I would almost always use the shard region proxy for that. That way you can go ahead and take advantage of the fact that if those entities are being moved, your messages will still be delivered once the sharding system is certain that those entities have been moved from point A to point B. Okay. Jose, you've been patiently waiting on YouTube. I'm going to answer some of your questions real quick. Okay. I want to use Akka.NET in a WPF application. Does Akka.NET have a way to implement MVVM, or should we use another framework for MVVM? So Akka.NET has the ability, using what's called a synchronized dispatcher, to run on the UI thread. So you certainly could go ahead and use Akka.NET to, let's say, update a bindable view model without having to do any cross-thread dispatching, for instance, right? So that's one instance where you might want to, where you can go ahead and use Akka.NET, but Akka.NET doesn't have its own MVVM framework, for instance. That's something that you probably want to go ahead and use maybe in combination with a library like Prism, for instance, or Shiny.NET. Okay, Michael King. Have you done performance testing against other actor systems? Some of my colleagues did a performance comparison between Akka.NET and Orleans, and it was found that Akka.NET was nearly 7 times slower in one benchmark, activating and calling a new actor from sharding. 1.5 milliseconds versus 229 microseconds, and had 5.6 times less throughput in one test, peak throughput of messaging through a remote node of 246K messages per second versus 147K messages per second. Is this something that you would expect to see? This was done in version 1.418 of Akka.net. We do continuously basically kind of work on our Akka.net performance testing as far as trying to make sure Akka.net's performance is as high as possible. Looking at those numbers there, in terms of the activating and calling a new actor from sharding, I need to see how the benchmark was set up, because it's possible that a lot of the overhead of Akka.net might be somewhat front-loaded onto there. And it would also depend a little bit on what systems are being used to go ahead and activate the sharding system versus like if you're using D-Data for that versus Akka.Persistence under the covers. Now, as far as the peak throughput of messaging through a remote node, I'd want to go ahead and see what that looks like, because that's very surprising to me. In most of our benchmarks against Orleans, Akka.net's performance in terms of end-to-end messaging throughput has been significantly higher than theirs. So I'm a little surprised to see that. That'd be something I'd want to go and take a look at, because things like your choice of serializer can actually impact that quite a bit. So that'd be one thing I definitely want to go and take a look at. But we're always in the business of trying to get faster and faster all the time, because that is a major point of competition, not just between the frameworks, but it's also a value add to our actual end users as well. We want to be in the business of making sure that our users have to run Akka.net on as little hardware as possible. Making sure our networking systems can perform that quickly is really of utmost importance for that. So that's why, by the way, one of the reasons why we're investing in Akka.net 1.5 of trying to go ahead and redo our whole networking system. The classic Akka.remoting system we're built on top of was not really built for speed. It was ported from the original sort of Scala project. The new protocol that we're going to take a look at, which is this artery system, should be a lot faster, on the order of like 1 million messages per second. So that's something that we're always continuously trying to work on. How come I suggested protobuf and not Hyperion? Because I fundamentally think reflection-based serialization is a foot gun and will eventually cause problems. I prefer to use schema-based serialization. Hyperion is fine in terms of being able to, it's much more performant than JSON.NET, for instance, but it will eventually create problems down the road. So I tend to personally prefer to use schema-based serialization because it's more performant. It's ultimately more robust from a versioning standpoint. And on top of that, it tends to use fewer bytes on the wire as well. Okay, in a recent training I had, you've mentioned type-safe actors. Do you have an ETA for the above feature? That's going to be next year. That's going to be part of Akka.net 2.0. It's going to be the first really major version upgrade we've ever done to Akka.net since 2015. And that's going to basically introduce typed actor references, which should be a major improvement over Akka.net. It solves one of the biggest drawbacks that Akka.net has, which is that you lose type cohesion when you read it right now. So that's something that we're going to be working on basically beginning of next year. Okay, Fabio, in the documentation, you talk about Hyperion serialization becoming the default, which is not schema-based. You prefer using protobuf for network messages. So one of the few areas where Akka.net still uses magic, where it probably shouldn't, is in our serialization system. That's because we want you to be able to get up and running quickly with Akka.net and not have to sit down and write a serializer first before you see Akka.remote get up and running. So we're looking to basically, we had discussed a long time ago, moving to Hyperion rather than using JSON.NET, because JSON.NET is just so dog slow and it's a common daemon dependency. So that's one of the reasons why we're taking a look at that. Hyperion is quite a bit faster than JSON.NET, and it's really good at polymorphic serialization, and we do have a large number of people using it. So we're still looking at basically making that the default replacement for JSON.NET in the future. Okay. Can you post more examples of actor communication through Akka.remote? We have a bunch in the main Akka.net repository, actually. If you go take a look in the samples area, we have the chat sample, which is pretty good. And then we also have the remote ping pong sample, which is our primary benchmark for being able to go ahead and measure performance through Akka.remote serialization. Let's see, should we use the default D-Data state store model or the persistent one? I would always use the D-Data one unless I had a compelling reason not to. That way, because basically if you end up, let's say, completely shutting down your sharding system and then restarting, you have to go and clean up the persistent store, which can be quite a pain in the ass. So I would almost always recommend just using D-Data for that. What about a Dapper comparison? Let's see. Well, Dapper is Microsoft introduces about one new distributed actor system framework per year by my count since 2015. This is one of their, it's not their most recent one, but it's one of their newer ones. Dapper actors aren't really actors. They're kind of a facade over their RPC system. And this is kind of meant to be a cross-platform way of being able to go ahead and build distributed systems. It's modeled really heavily after Azure Service Fabric is kind of the model that it follows there. I haven't really studied it all that closely. It's very Kubernetes specific, a lot of it as well. It seems to be getting a lot of attention from Mark Russinovich and some of the big dogs on the Azure team. But I don't really know a lot about what it's like building an application with one, because I've never actually sat down to use it. But I would say that if you want to try to build cross-platform, cross-language actor systems, Dapper would probably be the tool I would look at for using that. Tiago, the latest versions of Akka brought several new features. Do you have a forecast when you update the Petabridge training and bootcamp as well? We were going to try to go ahead and get some new courses done this year for the Akka.NET training. And we just recently updated Bootcamp to take advantage of .NET Core. We did that earlier this year. Right now, the biggest thing that we're updating is our Akka.NET clustering course, which introduces a whole bunch of different new facets. We're in the process of basically introducing that. We're in the process of standardizing basically kind of standardizing the way we teach people how to actually start up and host Akka.NET applications using some of the Microsoft.extensions.hosting libraries and that type of thing. I don't have an estimate for when those are going to be done necessarily, but it is something that we're actively working on, because the Akka.NET Bootcamp is kind of the gateway through which most people learn Akka.NET. And so it's in our interests, both as a business and as a project, to make sure that's continuously sort of up to date. And it's quite a bit behind right now. So we'll probably end up revisiting that. My guess would be sometime this fall will probably be when we visit Bootcamp. As for the Petabridge training courses, we do want to try to replace those altogether. The clustering course will stay intact with some updates. The design patterns of the remoting courses will probably be replaced by some higher level things, such as doing some, let's say, domain-driven design and streaming work with it. Okay. Is it possible to communicate from an actor in one cluster to an actor in another? Yes, you can do that via Akka.remote. That'll allow you to do that. Let's see. What settings defines a cluster router versus a router? Well, if I go back to my slides here, I go backwards in time. This might take a second. Let's see. In fact, you know what? Let me see if I've got the slide picker here. This is what defines a cluster router right here, is this little cluster enabled equals on section. That turns a router into a clustered router. So that's where that all comes from right there. If this cluster.enabled setting is off, then it's going to behave just like a normal local router all over again. Okay, next question. To deploy a router, Akka.remote, to deploy a router via Akka.remote, is the allow local routes setting to be used. So allow local routes is always set to on. What this means is that if this router, if the node creating this router is also a crawler node, this means I want to create a routee that is on myself, in addition to creating one that's remote over the network. So that's something that's always going to be included in there. If the allow local routes is set to off, it means that regardless of whether I satisfy this role criteria, I am never to have a routee on myself at all. That's what that means. All right. Is there a way to reliably passivate actors that are subscribing to a mediator over a pub sub that will allow them to recover when a new pub sub message is received? That's a fantastic question. And it's one of the trickiest things with Akka.Cluster Sharding right now. What we're going to go ahead and introduce, we currently have, so currently the roadmap is to do this as part of Akka.NET 2.0, but I kind of want to do this a little bit sooner. We're going to introduce a new type of actor reference called, it's a entity ref, which basically is a pointer to where this actor lives in Akka.Cluster Sharding. You can hold on to that entity ref forever. It doesn't behave the normal semantics of other actor references, but basically every time you send a message to that entity ref, it'll recreate that entity actor regardless of whether it exists or not. And you can basically subscribe that to the pub sub. So we might try to introduce that sooner rather than later, just because all the typed actor stuff we want to do is an additional layer of overhead on top of that. So we might do that a little bit sooner rather than later. But that's part of the solution there, is this new entity ref system. Because right now, in doing what you're asking here is a lot trickier than it should be. So having an entity ref system that allows you to decouple the actual reference to the actor that is alive right now is Akka.Cluster Sharding from having a persistent handle to that actor, whether it's alive or dead. That's something that we need to do. Okay, let's see. Okay, is there a way to handle distributed transactions? Let's say balance transaction plus shopping cart transaction occurring on the respective actors. There really isn't any notion of distributed transactions in Akka.net right now, other than through, let's say, a messaging protocol. What I would basically go ahead and do to manage something like that would be, and we have a blog post that talks about this, is using a bit of a Saga or a process manager pattern, where basically you'd basically go ahead and model your Saga as a finite state machine. During the stage where you're doing the commit, you have to have both parties reply back with a positive acknowledgement. If one of them times out or doesn't reply back, you would want to go ahead and actually essentially do a compensating transaction to perform a rollback. That would be kind of the way we'd recommend doing that today. We don't really have a plan for introducing things like transactions inside entity actors. That's kind of a little bit more higher level than what we do. Distributed data, which is like the sort of eventually consistent approach for doing that, is something that we're going to continue to support and build upon. But that's not the right tool for something that requires a transactional type component like that. Let's see. Gustavo, many thanks for Aaron for all you're doing. Oh, happy to help. Let's see. About Michael King's question on Orleans, I did the same application on Akka and Orleans, and Akka was much faster. Specifically in real-world scenarios, because Orleans induces you to await tasks to handle errors, for example, therefore creating contention on the communication path. Yeah, that's the sort of thing I've heard from users before who've tried Akka.net and Orleans together, is that usually Orleans is the one with a lot more overhead, which makes sense considering what's being managed behind the scenes there. Let's see. Gustavo, message pack, although it is not schema-based, seems to be performing faster and smaller than protobuf. Message pack actually is kind of an interesting hybrid between polymorphic, which means it uses reflection, and it also uses, what's it called? Tends to perform pretty well with, it does schema-based serialization and polymorphic serialization. So message pack supports a bit of both. Okay, and last question we're going to answer from Nicholas Frelat. Does Akka.Clustering help Akka.Remote to handle network communication issues? I'm referring to quarantine issues. The biggest thing that Akka.Cluster helps with is that when it detects a failed node, Akka.Cluster's heartbeat system and failure detection system is much more robust than what Akka.Remote does on its own. Akka.Remote has a simple binary, like, is this node available or not, sort of check, whereas Akka.Cluster is able to check with a consensus of other nodes. Now, when a node gets quarantined in Akka.Remote, this means that node failed to respond to a system message appropriately. Right now, we have a bit of an issue with the way Akka.Remote's designed, where that node is fundamentally unreachable once it gets quarantined. If you use a split brain resolver, Akka.Cluster will automatically kick that node out of the cluster, and that should force the node to restart if it's being supervised by a process manager like Kubernetes or a Windows service. That's how that should be answered. Last question I'll go ahead and address from Jose Silva. Does Akka.net work well with reactive UI? In my most recent Blazor application that I've been working on, I've been able to integrate Akka.net with iObservables. And in fact, we do have some connection between those and Akka streams. But working with the reactive UI library specifically is not something I've done. I don't see any reason why Akka.net wouldn't work well with it. We do have that built-in iObservable bridge in Akka streams, for instance, where you can go ahead and take messages that are being sent by actors and immediately turn them into events. Okay, last question. So when running Akka.net and Kubernetes, there should not be load balancing because you discourage it at the beginning. You can have load balance. Let's say, for instance, you have, if I go back to, let's say, my web crawler example, grab this real fast. Let's see if I can find this. Actually, you know what? I'll go ahead and use a sample from one of the slides I hid in the interest of time. This is part of the design of SDK bit down here. So these user service instances, these are all running under a load balancer in Azure Kubernetes service because they actually handle live traffic from end users, but they're also part of my Akka.NET cluster. Well, so for instance, when a user runs their credit card and we use Stripe as our payment processor, Stripe will send a webhook back if that payment clears or if it gets failed for some reason. Like if someone didn't enter in the right 3D chip data, like or the right CVS code or whatever it's called, Stripe will go ahead and let us know if that succeeded or failed. Well, this will go ahead and send a notice basically down here that when the user starts their payment, we go ahead and create this basically like intent ID down here. When that payment gets cleared, we go ahead and we basically execute on the fulfillment service here, the delivery of that user's product. So we have a load balancer up here, but we don't have a load balancer between these two services. That's what I meant by that. Is it still okay to have a load balancer? You just don't want someone sitting in the middle of these services right here. You can have it sitting above your cluster here, just not in the middle of it. All right, well, that'll do it for today's webinar. We'll probably be sending out an email with a link to the recording, which will be on YouTube. In fact, we've actually been streaming it live there this whole time. Thank you very much for attending today. If you have any questions, please feel free to reach out to us. Would love to go ahead and help you. And also bear in mind, we do have those clustering trainings coming up. So thank you very much for your time today. And I really appreciate your support. And thanks for watching. Take care.